Geological catastrophes are powerful and destructive events that can dramatically alter the face of our planet in a matter of moments. They occur within the grand and slow-moving flow of geological time, where billions of years coalesce into a complex mosaic. These catastrophes, whether earthquakes, volcanic eruptions, or landslides, are an integral part of the dynamic process of Earth's formation. Over millions of years, tectonic plates slowly move, collide, and diverge, creating mountain ranges and oceanic trenches. It is in these moments when nature's forces escape control that catastrophes occur, each lasting only a few seconds but having consequences that can be felt for centuries. For example, a powerful earthquake can trigger a tsunami that devastates coastal cities, but after tens of thousands of years, new ecological balance can emerge from the ruin. This is a reminder that destruction and creation go hand in hand. The geological timescale, spanning billions of years, allows us to view catastrophes as brief flashes in an endless stream of changes. Despite its destructive events, Earth continues to evolve, forming new landscapes and ecosystems that might not have been possible without these catastrophes. For instance, many volcanic islands, such as Hawaii, were formed over centuries by the long-term activity of underwater volcanoes. Each eruption, each tectonic event is not only destruction but also the beginning of something new, leading to the formation of unique ecosystems and landscapes. When we look at the layers of rock, we see the history of Earth written in stone, where each layer is a testament to one of these catastrophes that occurred over millions of years. Geological catastrophes serve as a reminder that Earth is a living organism, constantly changing and evolving, where destruction can lead to new growth. Millions of years after catastrophic events, nature recovers and new species emerge, adapting to the changed conditions. This relentless and majestic power of nature demonstrates its ability to restore itself. For example, after the devastating eruption of Vesuvius in 79 AD, nature was able to restore life on these lands, forming fertile soils that today support a rich agriculture. Thus, each geological catastrophe does not merely destroy but also creates conditions for the future. In this context, catastrophes become not just sources of pain and fear, but also necessary stages in the long history of the planet. These events, occurring in geological time, remind us of the grandeur of Earth and its ability to transform, where each catastrophe is but a moment in the endless process of formation and evolution. In this grand flow of time, catastrophes, despite their destructiveness, become milestones on the path to a new, unknown future where life always finds a way to adapt and continue its existence. Facts about geological catastrophes show that Earth is not just a lifeless planet, but a dynamic system where every element is interconnected and where destruction can become the foundation for a new beginning. From a gas-dust cloud that formed around 14 billion years ago after the Big Bang, the process of our planet's formation began. This cloud consisted of particles of dust, gas, and other elements that slowly coalesced under the influence of gravity. Over millions of years, these particles collided with each other, forming larger bodies that gradually accumulated mass. During this period, known as accretion, the temperature on the surfaces of these forming bodies reached incredible values, exceeding 1,000 degrees Celsius. Constant collisions between small bodies, asteroids and comets, created powerful explosions that released immense amounts of energy, turning the surface into a molten sphere of magma. Approximately 8 million years after the beginning of formation, massive impacts between bodies led to the formation of protoplanets, among which was our Earth. This primordial planet was a hellish world where rivers of lava flowed and the atmosphere was filled with toxic gases such as carbon dioxide and water vapor. The sensation of heat was unbearable, and each collision created new craters and mountains. In this chaos, order began to emerge. Layers of atmosphere formed, and the temperature gradually decreased. When Earth reached a size close to its current one, it continued to be bombarded by remnants of the protoplanetary disk, contributing to its further growth. Around 100 million years after its formation, the planet began to cool, and primary oceans started to form on its surface. These oceans, filled with water, were the result of the condensation of water vapor that was released from the hot mantle, an atmosphere. They created ideal conditions for the further emergence of life. By this time, Earth had acquired many geological features, such as continents and oceanic basins, which continued to change under the influence of tectonic processes. For example, around 2 billion years ago, the formation of the supercontinent Rodinia began, which existed for about 800 million years and played a significant role in the planet's history. This process of Earth's formation from a gas dust cloud is not just a story of how a planet came to be. It is an epic tale of the constant struggle between chaos and order, where each collision and drop of lava played its part in creating the world we know today. It is interesting to note that it was during this period that the foundations for the emergence of life on Earth were laid, which would begin to manifest billions of years later. The formation of Earth's primary crust occurred under extreme heat and chaos. Soon after the planet's formation, which took place around 460 million years ago, its surface was molten, resembling a vast ocean of lava. This flowing mass, composed of melted minerals, gradually covered the planet, forming the first continents. Over time, as the surface temperature began to decrease, the molten masses cooled, forming a thin, solid layer known as the primary crust. This process was uneven. In some areas, islands of solidified material formed, while others were subject to constant fractures and cracks due to internal forces from Earth's mantle. These forces often prevented the crust from settling, creating conditions for its fragility. The crust could be as thin as a few kilometers in some places, and its fractures were often the result of powerful volcanic eruptions that spewed magma onto the surface. It is important to note that during this period, the atmosphere was not suitable for life. It consisted mainly of carbon dioxide, ammonia, and methane, making it extremely aggressive. As soon as the crust cooled enough to no longer emit a glowing heat, it descended into darkness, creating dark spaces where life had not yet begun. This cooling process took millions of years, and it was not until around 3 billion years ago that more stable continents began to form on the surface, serving as the foundation for further life development. The primary crust, like a fragile film, was constantly subject to changes, but it became the very foundation upon which all of Earth's subsequent geology developed. Approximately 3 billion years after its formation, the first signs of life appeared on Earth, beginning their existence in oceans formed by the condensation of water vapor from the atmosphere. Approximately 4.5 billion years ago in the boundless cosmos, a colossal collision occurred between two planetary bodies, Proto-Earth and Theia, similar in size to Mars. These two celestial bodies, moving along their orbits, began to approach each other, their orbits gradually intersecting, as if in a slow dance under the influence of gravitational forces. At a distance of about 300,000 kilometers from each other, their attraction became increasingly noticeable and the speed of their approach increased. Ultimately, Theia, with a mass of about 10% of Earth's mass, struck Proto-Earth with immense force, equivalent to several million megatons of TNT. At the moment of impact, the temperature on the surface reached thousands of degrees Celsius, causing the evaporation of vast volumes of material that was ejected into orbit as a result of the catastrophe. This material consisted of molten rocks, metals, and other elements formed as a result of the destruction of the crusts of both planets. Over the following months and years, particles orbiting Earth began to coalesce, forming a disk of debris around the young planet. This disk slowly condensed, enveloping the entire celestial object, and over several 100 million years, it gave rise to the Moon, which became Earth's satellite. According to scientists, the Moon's mass is about 1/8 of Earth's mass, and its diameter is 3,800 kilometers. The process of lunar formation was not only chaotic, but also remarkably harmonious, as the collision created conditions favorable for the emergence of life on Earth. The presence of the Moon stabilized the axial tilt of our planet, contributing to the creation of a more predictable climate regime. It is believed that the Moon plays a key role in the tides and ebbs of the oceans, which are also linked to the processes of forming the first ecosystems. This cosmic event was not just a catastrophe, but the foundation for the formation of conditions necessary for life on the planet we call home. The collision between Proto-Earth and Theia was one of the most significant events in the history of our planet, determining its structure and dynamics for billions of years to come. After the collision of Proto-Earth and Theia, which occurred approximately 4.5 billion years ago, a cloud of molten material and debris began to form in space, slowly coalescing into a single body. In the first few tens of thousands of years following the catastrophe, particles composed of silicon, iron, and other chemical elements started to attract each other under the influence of gravity. This process, known as accretion, took place on Earth's orbit, where the temperature remained high and numerous small particles continued to collide and combine. Initially, the forming Moon was several times smaller than the present one, but over time, its size increased due to the continuous influx of material. About 100 million years after the collision, the forming Moon reached sizes comparable to the current ones, and its surface began to cool, forming a crust, and then the lunar seas, vast plains of solidified lava. This process was neither simple nor fast. For several hundred million years, the Moon continued to be bombarded by meteoroids, which affected its relief. During this period, craters formed, which we can observe today. The Moon, becoming Earth's satellite, had a significant impact on its rotation, slowing it down and stabilizing the planet's axial tilt. This stability was critically important for the formation of climatic conditions necessary for the emergence of life. The Moon's influence on the tides and ebbs of the oceans became a fundamental factor in the evolution of marine ecosystems, which in turn contributed to the development of life on Earth. The Moon, with its powerful gravitational field, not only affects the waters of the oceans, but also the atmosphere, creating pulsations that can influence weather and climatic conditions. Thus, the Moon, born out of chaos after the catastrophe, became a loyal companion of Earth, accompanying it for billions of years. Its surface height reaches 4,000 kilometers, and its diameter is 3,800 kilometers, making it the fifth largest moon in the solar system. Late, heavy bombardment occurring during the early stages of Earth's existence was a period when the planet was constantly subjected to the impact of meteoroids and asteroids. These impacts, often with immense force, altered the landscape, creating new relief forms and geological structures. Each meteorite entering the atmosphere not only destroyed but also triggered processes that led to the formation of new minerals, rocks, and even new ecosystems. Upon colliding with Earth, meteoroids could range in size from several meters to hundreds of kilometers in diameter, causing massive waves of destruction and ejecting enormous quantities of dust and gas into the atmosphere. These ejecta could block out sunlight, leading to global cooling and climate change, which in turn influenced the development of life. This was an era when Earth's surface was continually reshaped. Mountain ranges dotted with craters emerged, and oceans filled with minerals created by colliding streams of matter. Each new impact added to the planet's diversity, forming not only physical structures, but also chemical conditions necessary for the further emergence of life. Scientists suggest that such impacts could have enriched Earth with organic compounds, facilitating the emergence of the first forms of life. For instance, renowned geologist and planetary scientist David Kring asserts that meteorite impacts could have brought crucial elements like carbon and nitrogen into the oceans, which became the basis for biochemical processes. While Earth was subjected to these catastrophic changes, its landscape was constantly transforming, from molten lava fields to newly formed mountain ranges. As a result, Earth's surface became not just a stage for destruction, but also a place for the emergence of new forms of life and ecosystems adapted to the harsh conditions created by the constant impacts of celestial bodies. This was an era when every crack in the crust, every new mountain and every valley was a result of an unending process where destruction and creation went hand in hand, and Earth continually evolved under the influence of cosmic factors. Each meteorite impact was a catalyst for change, leaving its mark on geological history and laying the foundation for the future existence of diverse flora and fauna. The atmosphere of the earliest Earth was extremely hostile and alien to any living organism that could have imagined it. Around 4 billion years ago, the planet was shrouded in clouds of heavy gases such as carbon dioxide and ammonia, creating a dense veil that blocked out sunlight. There was virtually no oxygen in the atmosphere, and instead of the familiar blue sky, the planet was dominated by a reddish, turbulent expanse filled with electrical discharges that rose and fell like endless lightning on a wild, stormy sky. These discharges likely resulted from high concentrations of methane and other gases, creating conditions for chemical reactions that would later play a crucial role in the emergence of life. Such conditions ensured constant thunderstorms that rained down on the surface, transforming it into a pulsating world where every moment was charged with intense energy. Surface temperatures reached cosmic levels, fluctuating between 100 and 200 degrees Celsius, creating volcanic landscapes that spewed lava and gases that mixed with the sky, forming thick clouds and acidic rain. In these conditions, there was no life as we know it, but it was here that the foundations for future development were laid. Scientists like Dr. Stephen D. Sullivan, studying samples of the oldest minerals, found that in such conditions, active chemical evolution was taking place, producing organic molecules that could eventually become the precursors of life. This process, known as abiogenesis, occurred in conditions that now seem completely uninhabited and hostile. Scientific research has shown that the first signs of life could have emerged in bodies of water filled with simple organic compounds that, under conditions of high temperature and pressure, could combine to form more complex molecules. It is important to note that at this stage, the Earth's atmosphere was so rich in carbon and sulfur that any forms of life that might have appeared would have faced invisible limitations that we do not see today. This world, full of energy and potential, was both a desert and a cradle for the future where the idea of life was born. Over millions of years, this atmosphere began to change, but that distant primordial period will forever remain in the memory of our planet. Over millions of years, primary oceans gradually filled the depressions of Earth, creating the foundation for future life. These oceans formed due to water that came to our planet from comets and asteroids. Research shows that comets contain up to 80% water, while asteroids carry many minerals and organic compounds necessary for the formation of biochemical processes. Approximately 3,800,000,000 years ago, oceans already existed on Earth, filling the depressions formed by volcanic activity and tectonic processes. Primary water had a saturated color ranging from greenish to brownish due to the large amount of suspended particles and dissolved minerals. These minerals, such as sodium, calcium, magnesium, and potassium, along with various salts, gave water a specific chemical composition, conducive to the formation of complex molecules. It is important to note that this very composition of water acted as a catalyst for the first chemical reactions, which led to the processes that resulted in the formation of the first simple organisms. This primary ocean was not just water, but a complex environment rich in organic compounds such as amino acids and carbohydrates, which are the building blocks of life. Scientific data indicates that in these conditions, processes began that later led to the formation of cells and, consequently, to the development of life in the form we know it today. These primary oceans served as a kind of laboratory where various chemical reactions occurred under the influence of solar light and heat emitted from the planet's interior. Around 3 billion years ago, when the oceans reached their maximum volume, they became an ideal environment for the emergence of the first living organisms, which began to use solar energy for photosynthesis. These processes not only changed the chemical composition of the atmosphere, but also led to the appearance of oxygen in the oceans, opening new horizons for the evolution of living beings. Primary oceans, rich in chemical substances and minerals, became the cradle of life, providing the necessary conditions for its origin and development. These oceans were full of mysteries, and each new discovery in the fields of geochemistry and biology helps us better understand how life could have emerged from this primeval mixture. As scientists study these ancient waters, they uncover new facts that testify to the complexity and diversity of the process of the origin of life on Earth. The Earth's crust is composed of numerous large and small sections that move across the planet's surface like a mosaic of moving plates. These sections, known as tectonic plates, slowly drift, altering the face of the Earth over billions of years. The movement of the plates occurs at a speed of just a few centimeters per year, which seems insignificant, but over millions of years, it leads to significant changes in the landscape. This process, known as plate tectonics, is governed by convective flows in the Earth's mantle. The mantle, located beneath the crust, consists of molten rocks that slowly rise to the surface and sink back, creating movement that facilitates the shifting of the plates. At the boundaries of the plates, various geological processes occur, such as the formation of mountains, earthquakes, and volcanoes. For example, when two plates collide, one may rise, forming mountain ranges, while the other sinks into the mantle, resulting in the formation of deep oceanic trenches. These processes have been occurring for billions of years and have shaped continents, oceans, and other geological structures. One example of such long-term change is the uplift of the Himalayas, which began around 50 million years ago when the Indian plate collided with the Eurasian plate, causing powerful seismic and volcanic activities. This collision continues today, and the height of the mountains continues to increase. Plate tectonics is the key to understanding the geological history of the Earth, as it explains how continents have moved, merged, and separated. Scientific research shows that despite the slow pace, these movements have a significant impact on the climate, ecosystems, and the development of life on the planet. For instance, changes in the position of continents can affect ocean currents and climatic conditions, which in turn influence biodiversity. Evidence of tectonic movements can be found in the distribution of fossils, rock formations, and even in the forms of life that have emerged and disappeared in response to changes in the environment. Therefore, plate tectonics is an integral part of the dynamic system of the Earth, where every millimeter of movement can lead to global changes over millions of years. Scientific research, such as that conducted by American geophysicist Raymond Slater in the mid-20th century, has helped develop the theory of plate tectonics by combining data on earthquakes, volcanic activity, and the distribution of fossils. These studies enable scientists to more accurately predict geological changes and understand how the Earth will look in the future. Interestingly, in recent decades, the observation of plate movements has become possible thanks to satellite technologies, which provide precise data on how quickly and in what direction the tectonic plates are moving. For example, satellites like GPS track changes in the position of the plates, allowing scientists to monitor their movement in real time. These data not only aid in scientific research, but also in assessing risks associated with earthquakes and other geological phenomena, which can save lives and reduce damage from natural disasters. An example is Japan, where active seismic monitoring and the study of tectonic processes help prepare for earthquakes and minimize their consequences. Ultimately, the tectonic activity of the Earth is not just a geological process, but a vital element of the system that supports life on the planet, shaping its surface and creating conditions for the existence of various ecosystems. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This process occurs in subduction zones, which are typically located at the boundaries of oceanic and continental plates. One of the most well-known subduction zones is the Peruvian subduction zone, where the Nazca Oceanic Plate descends beneath the South American continental plate. This process begins when two plates collide and the heavier oceanic plate starts to slowly sink beneath the lighter continental plate. Tension between the plates accumulates over many years, sometimes even decades, creating immense pressure at the boundary. This pressure can reach up to 1 million tons per square meter. When this tension becomes too great, a rupture occurs and the plates suddenly move, causing an earthquake. On the Richter scale, such earthquakes can range from 5 to 9 magnitudes, depending on the amount of energy released. Earthquakes in subduction zones are particularly destructive, as they can generate not only seismic waves but also tsunamis. For example, the earthquake in the Indian Ocean in 2004, known as the Indian Ocean earthquake, had a magnitude of 9 and caused a tsunami that took the lives of more than 200,000 people in 14 countries. The pressure accumulated during subduction also leads to volcanic activity. When one plate descends, it heats up and begins to melt, forming magma. This magma rises to the surface, creating volcanoes. Volcanic activity in subduction zones can be extremely destructive. For instance, the eruption of Krakatoa in 1883 was one of the most powerful in history. It caused global climate changes and resulted in significant casualties. It is important to note that the process of subduction is the primary mechanism that shapes the Earth's surface. It is responsible for the formation of mountain ranges such as the Andes and the Himalayas, which arise from the collision of tectonic plates. Such processes have been occurring for millions of years and continue to shape the Earth's surface and influence life on it. Ultimately, understanding the processes of subduction and their consequences helps scientists better predict earthquakes and volcanic eruptions, which can save lives and reduce the damage from natural disasters. For example, in Japan, where subduction occurs between the Philippine and Eurasian plates, active seismic monitoring is conducted, and research into tectonic processes helps to predict earthquakes in advance, significantly increasing the level of safety for the population. Spreading of the ocean floor is a process that occurs at the boundaries of tectonic plates, where magma rises from the Earth's depths through cracks in the ocean floor and solidifies, forming new crust. In these areas, known as ridges such as the Mid-Atlantic Ridge, magma rises from the mantle at a depth of about 200 kilometers. This process was first described in the mid-20th century when scientists began actively exploring the ocean floor using submersibles and sonars. When magma reaches the surface, it encounters cold ocean water, causing it to harden instantaneously and form new rock types, such as basalt. For example, in the vicinity of Iceland, spreading occurs so intensely that the island increases in size by several centimeters each year, and underwater volcanoes like Surtsey continue to form, creating new land areas. The temperature of the magma when it reaches the surface can reach around 1200 degrees Celsius, which contributes to the formation of active volcanoes. At such moments when magma emerges, the underwater world is filled with clouds of steam and gases, creating an atmosphere filled with energy and chaos. This process also leads to the formation of deep cracks and faults that can reach several kilometers in width and tens of kilometers in depth. In the darkness of the ocean floor, new Earth's surface is born, and this activity spreads the continents. One of the most striking examples is the spreading of the South American and African plates, which occurs at a speed of about 2 centimeters per year, which is quite rapid for geological processes. As a result of spreading, new ocean basins are formed, and their sizes can change over millions of years. For example, the Atlantic Ocean is approximately 100 million years old, and its expansion continues. This process also contributes to the formation of hydrothermal vents, which are ecosystems teeming with unique organisms such as tube worms and bacteria that can survive in extreme conditions. Their study helps scientists understand how life can exist in environments far removed from the ones we are familiar with. Spreading of the ocean floor is not just a process of forming new crust, but also a driving force that shapes the landscape of our planet, creates new ecosystems, and influences the climate. Oceanic plates that move and interact lead to the formation of mountain ranges such as the Himalayas, which arose from the collision of the Indian and Eurasian plates. This process continues, and every second numerous changes occur beneath our feet, ultimately altering the face of the Earth. Supercontinents are vast landmasses that form as a result of tectonic processes involving the merging of separate continents and subsequently break apart. This process is cyclic and occurs over millions of years, leading to the formation and dissolution of supercontinents on our planet. Throughout Earth's geological history, several supercontinents have existed, each exerting a significant impact on climate, ocean currents, and the evolution of life. When continents unite to form a supercontinent, it leads to changes in global climatic conditions. For instance, the union of land masses creates large interior regions where the climate can become more continental, reducing rainfall and altering vegetation. Meanwhile, on the periphery of the supercontinent, humid tropical climatic conditions can arise, fostering the development of rich ecosystems. The movement of continents also affects ocean currents. When land masses unite, it changes the directions of currents, potentially leading to the formation of new marine ecosystems. For example, when continents were united, warm and cold ocean currents could move differently, influencing the distribution of marine life and creating unique habitats for many species. Periods of isolation that occur during the breakup of supercontinents create conditions favorable for the evolution of various species in different directions, leading to the emergence of new species and changes in ecosystems. When supercontinents begin to break apart, they create new oceans and maritime passages that connect previously isolated ecosystems. For instance, the breakup of supercontinents led to the formation of new oceans, such as the Atlantic Ocean, which emerged after the breakup of Pangaea around 200 million years ago. This interaction between isolation and connection of ecosystems creates complex network relationships between species, contributing to the diversity of life. An example can be seen in the more recent unification of continents into a hypothetical supercontinent, where conditions arose that allowed different ecosystems to interact, exchange species, and alter their characteristics. Thus, supercontinents are a crucial element of global geological dynamics and play a key role in shaping climate and the evolution of life on Earth. Scientific research indicates that the supercontinent cycle occurs approximately every 300 million years, indicating ongoing changes on the planet. Specific information about the time when supercontinents existed varies, but according to geological data, the last supercontinents, such as Pangaea, existed at the boundary of the Permian and Triassic periods, around 200 million years ago. This time was characterized not only by changes in geography, but also by significant mass extinctions of species related to rapid climatic changes. For example, the mass extinction at the end of the Permian period, which wiped out up to 95% of all species, occurred precisely due to changes caused by tectonic processes. Therefore, supercontinents not only shape the physical structure of our planet, but also influence biological diversity, climatic conditions, and evolutionary processes that occur on Earth. The process of land unification and disintegration is not just a matter of tectonic changes, it is the true history of life on our planet, which continues today. Each new stage of supercontinent formation brings changes to ecosystems, climate, and even how we understand our planet. Supercontinents form continental and oceanic structures that influence atmospheric and oceanic circulation, which in turn can affect global temperature and climatic conditions. Pangaea was a supercontinent that existed around 250 million years ago and began to break apart approximately 175 million years ago. This continent had a unique shape resembling a giant letter S, stretching from the northern to the southern pole. In the center of Pangaea lay a vast landmass surrounded by an ocean known as Panthalassa. The climate on Pangaea was extremely diverse but also harsh. The interior regions of the continent were arid with high temperatures that could reach 35 degrees Celsius in the hot months. This created conditions for the formation of large deserts, such as the Tethys Desert, which was located where the modern Mediterranean Sea is now. Monsoon winds blowing from the oceans brought abundant rain to the coasts, creating wet tropical forests in some areas. However, most of Pangaea did not have a temperate climate, which excluded the presence of the rich flora and fauna typical of today. Instead, the continent was dominated by various types of reptiles and primitive plants like ferns. The largest animals of that time, such as dinosaurs, appeared during this period because the conditions for their development were very favorable in the warmer, wetter regions. However, in the central part of Pangaea, where the climate was the harshest, survival was difficult and the ecosystems were less diverse. The global climate was less predictable due to the enormous size of the supercontinent, which hindered air circulation, causing sharp temperature fluctuations. Scientists like Professor David Grant studied geological samples from this period and concluded that the absence of large water bodies in the center of Pangaea contributed to the emergence of extreme climatic conditions. Pangaea was a significant stage in the geological history of Earth because its existence facilitated the exchange of species between different regions that later separated due to tectonic activity. Scientific data show that it was during this time that the formation of modern continents began, as evidenced by the discovery of fossils identical on different continents, such as South America and Africa. These findings, such as dinosaur remains and plants, indicate that Pangaea was indeed a single entity, and along with climate changes, it led to changes in the biosphere. The process of Pangaea's disintegration began approximately 180 million years ago, when a single supercontinent began to slowly drift apart, giving birth to new oceans and seas. This process lasted for tens of millions of years and was driven by tectonic activity as moving subterranean plates began to separate from one another. Initially, continents began to drift apart by small distances, forming narrow waterways that later expanded into oceans. For instance, the Atlantic Ocean formed as a result of continental drift that started around 130 million years ago. During this geological process, which scientists refer to as continental separation, new seas were formed. An example is the Tethys, which existed between present-day Europe and Asia and gradually narrowed until it disappeared. During this time, continents such as North America and the European part of Asia began to slowly move away from each other at a rate of several centimeters per year. This movement was both monumental and slow, and over millions of years it led to the formation of vast oceanic basins. Initially, the narrow seas that formed served as channels for the migration of ancient marine organisms, such as ammonites and belemnites, which adapted to the new conditions. Meanwhile, on land, numerous changes were occurring. The climate was changing, and ecosystems were evolving to adapt to the new realities. For example, while tropical forests existed in the southern part of Pangaea, the northern part was becoming more temperate, which facilitated the development of various forms of life. Throughout this period, tectonic plates continued to move, and eventually significant rifts occurred, opening new oceans. For instance, the Indian plate began to move northward, colliding with the Eurasian plate, which ultimately led to the formation of the Himalayas. This collision was not only a physical but also a catastrophic geological process, as it caused earthquakes and volcanic activity. The process of Pangaea's disintegration was not linear and passed through numerous stages, including periods when continents could temporarily come together and then drift apart again. For example, around 100 million years ago, North America and Europe were closer to each other, forming vast continents with unique ecosystems. However, over time, the distance between them increased, and after several million years, they found themselves at a significant distance from each other. The separation of Pangaea also led to changes in ocean currents, which began to form based on new continental configurations. This change in oceanic flows affected the climate conditions on Earth, which in turn contributed to the evolution of various species. For example, the formation of the Gulf Stream, which carried warm water from the equator to the northern latitudes, altered the climate in North America and Europe. Tectonic movements continue today, and this means that the Earth is still changing. Scientific research shows that in the future, continents will continue to drift apart, and through millions of years, we may see a completely different map of the world. For instance, according to geologists' predictions, Africa may collide with Europe again in approximately 200 million years, creating new mountain ranges and altering the climate in that region. Over this time, significant changes have occurred on Earth, and each stage of Pangaea's disintegration has left its mark on the planet's history. Scientific data and geological findings, such as the matching of fossil remains on different continents, confirm that the process of Pangaea's disintegration was not only a crucial stage in Earth's history, but also the foundation for the creation of diverse ecosystems that we observe today. The formation of the Atlantic Ocean began approximately 100 million years ago when continents began to move apart, gradually separating as Pangaea broke up. Initially, a narrow strait between Africa and America gradually widened, eventually forming an ocean that grew in size with each passing million years. Around 100 million years ago, during the Cretaceous period, the formation of new oceanic crust contributed to the development of rift zones, leading to the emergence of the first ocean currents. These currents, such as the Gulf Stream, began to form due to differences in water temperature and salinity, as well as the influence of winds. As the ocean expanded, the climate in the surrounding continents changed. Warmer and more humid conditions in the tropics led to the formation of tropical forests, while colder regions, such as the northern coasts of Europe and America, became harsher. The changes in ocean currents in the North Atlantic had a significant impact on the climate, contributing to the migration and evolution of marine species. For example, the development of the Gulf Stream caused warm waters to circulate along the eastern coast of North America, influencing the lives of marine organisms such as fish and mollusks, which adapted to the new conditions. Meanwhile, colder waters in the north became home to other species such as tuna and cod, leading to the diversification of marine ecosystems. The increase in the size of the Atlantic Ocean also led to the creation of new maritime routes, facilitating the exchange of species between continents. For instance, the migration of marine mammals and fish through new straits created unique ecosystems, such as coral reefs in the Caribbean Sea. Currents like the Labrador Current, which carries cold waters from the north, also influence the climate and ecosystems of the coasts from Greenland to New England. By the end of the Cretaceous period, when the Atlantic Ocean reached its current size, new conditions emerged for marine life, contributing to the development of both local and migrating species. Thus, the Atlantic Ocean became not only a significant geographical object, but also a key factor in the evolution of life on Earth. The structure of the ocean floor, formed by various geological processes such as volcanism and plate tectonics, also created unique conditions for the habitation of marine organisms, such as hydrothermal vents, which provide access to energies and nutrients for various ecosystems. Volcanism is a complex process by which the internal energy of the Earth finds its way to the surface through cracks in the crust. This energy accumulates as a result of the constant decay of radioactive elements such as uranium and thorium, as well as heat generated by pressure on the lower layers of the Earth's crust. The temperature in the mantle, where most of these processes occur, can reach around 1,200 degrees Celsius. As a result of this heating, rocks become plastic and begin to move. When the pressure becomes too high, the molten rocks known as magma break through the crust and are ejected onto the surface. Volcanism is a manifestation of the constant tension between the internal forces of the Earth and the crust that holds them back. These forces have been acting for millions of years, shaping the landscape and changing it. For example, in some regions, such as Iceland, located on the boundary of tectonic plates, this tension is particularly noticeable. Here, magma rises to the surface through cracks, creating new land areas. Volcanism not only shapes the relief, but also makes a significant contribution to the composition of the atmosphere and hydrosphere. Eruptions release large volumes of gases into the atmosphere, including carbon dioxide and sulfur, which can affect the climate on Earth. Volcanic gases entering the atmosphere can form clouds that then affect solar radiation, reducing the temperature on the planet. At the same time, volcanic activity enriches the soil with minerals, contributing to the development of ecosystems. Each time an eruption occurs, not only magma but also various minerals, such as basalt and pumice, are ejected onto the surface, which are then used in construction and other industries. The constant interaction between the internal and external forces of the Earth creates a dynamic environment where volcanism serves not only as destructive, but also as a creative process. According to estimates, over the past 2 million years, more than 100 major eruptions have occurred, each leaving its mark on the Earth's surface and forming unique geological formations. Nevertheless, volcanism remains not only a geological but also a social phenomenon, as populated areas near active volcanoes are constantly at risk. Studies show that the concentration of people in such areas is associated with both fertile soils and the risks they pose. Volcanic activity serves as a powerful reminder that the Earth is not a static system, but a living organism, constantly changing under the influence of internal and external factors. Trap volcanic activity represents one of the most impressive geological processes, leading to the formation of extensive lava plateaus that can cover thousands of square kilometers. These eruptions occur due to tectonic processes when magma rises to the surface through fractures in the Earth's crust. A classic example of trap volcanic activity are the Siberian traps, which formed around 250 million years ago at the end of the Triassic period, coinciding with a mass extinction of life. Eruptions in this region over millions of years accumulated layers of lava, creating powerful plateaus such as the Siberian Traps Plateau, where the thickness of lava deposits can reach 1,000 meters. Lava flowing from fissures has low viscosity, allowing it to spread over significant distances, sometimes up to 300 kilometers from the eruption site. This results in stepped structures as each new layer of lava overlays the previous one, forming characteristic horizontal layers. These layers can be covered with various minerals and create unique relief forms, such as plateaus and hills, which can be observed in places like Canada, where lava plateaus formed as a result of trap volcanic activity. Such eruptions not only create geological formations but also influence climate, as the release of carbon dioxide and sulfur can affect the atmosphere. Over time, the Siberian traps have become a true laboratory for studying ancient ecosystems and climate changes, as they have preserved traces of diverse organisms that existed in those times. Additionally, it is worth noting that trap formations can serve as sources of valuable minerals. For example, in regions like Norway, where traps have formed, large deposits of nickel and copper have been found, highlighting the economic significance of these geological formations. Research shows that trap volcanic activity has a long-lasting impact on the surrounding environment, altering not only the landscape but also ecosystems, as new ecosystems form on fresh lava flows that gradually undergo weathering and enrichment with nutrients. This dynamism makes trap volcanic activity an important aspect not only of geology, but also of ecology, opening new horizons for scientific research and understanding the processes taking place on our planet. It is important to note that similar processes have occurred in other parts of the world, such as in India, where the Deccan traps formed approximately 65 million years ago also caused significant changes in ecosystems and climate. The formation of trap plateaus is not just a geological phenomenon, but a complex of processes that shape landscapes and influence life on Earth. Siberian traps formed around 200 million years ago as a result of intense volcanic activity represent some of the largest volcanic formations on the planet. These traps cover an area of more than 1 million square kilometers, comparable in size to the combined territories of France and Germany. Volcanic eruptions occurring over millions of years released enormous volumes of lava, resulting in the formation of multi-kilometer layers of basaltic rocks. Scientists suggest that during this period, not only were extensive plateaus formed, but significant changes also occurred in the Earth's atmosphere. Volcanic gases, such as carbon dioxide and sulfur dioxide, were released into the atmosphere in vast quantities, creating conditions reminiscent of a volcanic winter. The sky was obscured by volcanic ash, which blocked sunlight, causing temperatures on the planet's surface to drop and reducing photosynthesis, leading to mass extinctions. One well-known example is the Triassic extinction event, when approximately half of all living species disappeared. Studies indicate that these climate changes could have lasted for several tens of thousands of years. Scientific research conducted in recent decades has examined samples of rock extracted from the depths of the Siberian traps, revealing traces of ancient carbon isotopes, which indicate a sharp increase in carbon dioxide in the atmosphere. This led to significant changes in ecosystems and the biosphere of that time, as evidenced by fossil finds indicating the demise of many species and the adaptation of some to new conditions. The Siberian trap served as one of the catalysts for climate changes that led to the creation of new ecosystems and, ultimately, the formation of the modern appearance of our planet. These processes occurred against the backdrop of global changes affecting oceans and continents, and their effects were felt for millions of years after the volcanic activity ceased. Volcanic eruptions left a deep mark on the geological history of Earth, altering not only landscapes, but also the very atmosphere. The Siberian traps are not just a geological formation, but a whole historical epoch that played a crucial role in the formation of the biosphere on Earth. The height of the basaltic rock layers in some places reaches up to 2,000 meters, indicating the power of these eruptions and their significant impact on the planet. Siberian traps, which emerged around 250 million years ago, acted as a catalyst for one of the most significant mass extinctions in Earth's history, the Permian extinction. This phenomenon is linked to massive volcanic eruptions that released enormous volumes of carbon dioxide and other greenhouse gases into the atmosphere. According to research conducted by geologists from Stanford University, the eruptions emitted more than 1 billion tons of carbon dioxide, leading to a significant increase in its concentration. This change in atmospheric composition triggered global warming, with the planet's temperature rising by several degrees, which had a devastating impact on ecosystems. The increase in carbon dioxide levels led to ocean acidification, as the oceans began to absorb the excess carbon, causing significant changes in the chemical composition of seawater. Scientists from the Scripps Institution of Oceanography in California note that ocean acidification was responsible for the mass die-off of coral reefs and other marine organisms dependent on calcium. These changes affected not only marine life but also terrestrial ecosystems, as climatic conditions became less stable, exacerbating existing ecological problems. As a result, according to paleontologists, up to 95% of all Earth's living species perished within less than 2 million years. This event was the greatest catastrophe in the history of life on the planet, altering the course of evolution and opening the way for new forms of life. Volcanic gases released as a result of trap activity not only altered climatic conditions, but also destroyed familiar ecosystems, ultimately facilitating the emergence of new species adapted to the changed conditions. Traces of these changes can be seen in geological layers, where remains of organisms that perished as a result of this catastrophic event have been found. Complex ecosystems that existed before the Permian extinction were replaced by simpler structures, leading to long-term changes in the biosphere. Paleobiologists continue to study these processes, analyzing samples of fossilized material from various layers to understand how the extinction occurred and what mechanisms were behind these global changes. Mass extinctions represent one of the most dramatic and catastrophic processes in Earth's history, when a multitude of living organisms disappear simultaneously due to various factors. These events are not rare and have occurred several times on our planet, leaving behind devastated ecosystems and significantly altering biological diversity. Scientific research shows that mass extinctions can be caused by a multitude of reasons, including climate change, volcanic activity, asteroid impacts, and changes in sea levels. One of the most striking examples is the extinction event that occurred around 6 million years ago, when a rapid change in climate led to the disappearance of more than 50% of all species on the planet. During this time, global temperatures rose sharply, causing the collapse of ecosystems that relied on stable conditions. For instance, volcanic activity can release enormous volumes of sulfur and carbon dioxide into the atmosphere, leading to acid rain and changes in the chemical composition of oceans. Studies conducted by scientists like Dr. Alan H. Buehler show that such events can alter the composition of the atmosphere and cause abrupt changes in ecosystems. Additionally, collisions with large meteorites, such as the one that occurred around 65 million years ago, led to the mass extinction of dinosaurs. The impacts of these meteorites create massive waves of pressure and temperature that destroy living matter over large areas, triggering a chain reaction that affects food chains. As a result, the diversity of species is sharply reduced and ecosystems begin to recover only after millions of years. The study of fossils and geological layers allows scientists to identify traces of these catastrophic changes and understand how they have affected life on Earth. For example, in the deposits from the period of the dinosaur extinction, high concentrations of iridium were found, indicating the cosmic origin of the catastrophe. Thus, mass extinctions highlight the fragility of life on Earth and the vulnerability of ecosystems in the face of global changes, noting that even the most dominant species can be on the brink of extinction. These processes not only alter biological diversity but also shape the new face of our planet, as evidenced by geological layers that have recorded the history of life on Earth. Scientific research continues to uncover new details of these events, allowing us to better understand the mechanisms behind mass extinctions and their consequences for the future of life on the planet. For example, there is currently a hypothesis about the possibility of a sixth mass extinction caused by human activity, which threatens the existence of many animal and plant species. Among these threats are climate change, destruction of natural habitats, and environmental pollution, which could lead to new waves of extinction of living organisms. The Permian extinction, which occurred around 250 million years ago, is considered the most catastrophic of all known mass extinctions on Earth. Up to 96% of marine species and around 70% of terrestrial organisms disappeared, leading to massive changes in the planet's ecosystems. During this time, significant changes in climate occurred. The last period of the Permian was marked by a sharp warming and increase in ocean acidity. These factors acted as catalysts for the slow decline of life in the oceans. For example, corals, which formed the basis of marine ecosystems, began to die off en masse, severely impacting marine ecosystems as coral reefs provided homes for numerous other species. Simultaneously, entire groups of organisms such as trilobites and many brachiopods disappeared as they were unable to adapt to the changing conditions. On land, the situation was equally catastrophic. Forests composed of giant ferns and conifers began to disappear, giving way to open spaces, which led to the extinction of many terrestrial animal species, including large amphibians and reptiles. During this period, there was also a sharp decline in the diversity of mammals and the first dinosaurs, which could not survive in conditions where their usual food sources and shelters became inaccessible. All this led to the desolation of once rich ecosystems, which were teeming with life and diversity. As a result of this extinction, Earth lost a significant amount of biomass for many millions of years, creating conditions for the slow recovery of life and the emergence of new forms of organisms. Interestingly, it was after the Permian extinction that the Triassic period began, during which new ecosystems began to develop on Earth, although these were a completely different biological palette. For example, it was during this period that the first dinosaurs and mammals appeared, filling the ecological niches left vacant by the mass extinctions. The Permian extinction marked a significant milestone in the history of life on Earth, demonstrating how quickly ecosystems can change and how rapidly they can be destroyed. This event also became the basis for further research in paleontology and ecology, as scientists strive to understand the mechanisms that led to such a massive loss of life. Studies show that climate changes and ecological disturbances can be triggered by both natural and anthropogenic factors, underscoring the importance of monitoring and protecting existing ecosystems. Following the Permian extinction event, which occurred approximately 250 million years ago, Earth's ecosystems were on the brink of collapse. This event, which wiped out around 95% of all marine and 75% of terrestrial species, left the planet nearly empty. The disappearance of groups like trilobites, which dominated the seas, and many amphibian species that filled terrestrial ecosystems, left the remaining species in fierce competition for resources. In such devastated biomes, such as oceans, there was a sharp simplification of food chains. Only a few groups of organisms, such as fish and some mollusks, survived and occupied the newly available ecological niches. On land, reptiles took over and began to evolve in the new ecological realities. The time following the Permian extinction was a kind of reset for evolution, as the surviving species adapted to the changed conditions. This gave rise to a new era, the Mesozoic, in which dinosaurs became the key representatives of fauna. Approximately 3 million years after the extinction, in the Triassic period, the first dinosaurs appeared, rapidly developing and diversifying. At this time, marine ecosystems also began to recover, and by the Jurassic period, large predators like plesiosaurs and ichthyosaurs had re-established themselves in the oceans. The appearance of these new forms of life indicated that nature, despite the catastrophe, had begun to restore its biodiversity. Thus, a few million years after the Permian extinction, ecosystems began to fill with new forms of life, and the symphony of evolution resumed on the planet. During this time, many changes occurred, including the appearance of the first mammals and birds, which, although small compared to the dominant dinosaurs, laid the foundations for future diversity. By the end of the Triassic period, around 240 million years ago, ecosystems had become much more complex than at the beginning of the Mesozoic era, and new types of interactions between species began to form, heralding further evolution. Impact events refer to catastrophic collisions between Earth and large celestial bodies that can instantly disrupt the fragile balance of the planet. When asteroids or comets, ranging from several hundred meters to tens of kilometers in size, strike the Earth's surface, they not only create craters but also trigger chain reactions capable of destroying millions of lives and altering the climate for centuries. Upon impact, an enormous amount of energy is released, equivalent to the explosion of thousands of atomic bombs, leading to widespread destruction, fires, and the release of dust and gases into the atmosphere. This can result in a nuclear winter, where sunlight is blocked, causing a sharp drop in temperature and the death of vegetation. One such example is the presumed cause of the dinosaurs' extinction. A collision with a celestial body caused global changes in ecosystems, leading to the extinction of more than 75% of all species on Earth. Impact events can also initiate volcanic activity, resulting in lava and gas emissions that further contaminate the atmosphere and exacerbate climate conditions. Geological layers such as the KT, Cretaceous-Tertiary boundary, contain high concentrations of iridium, an element primarily found in meteorites, serving as indirect evidence of such collisions. These events underscore the vulnerability of the planet to cosmic forces and the unpredictability of the future, as even a small influence from external objects can have catastrophic consequences for life on Earth. Scientists continue to study these events to understand their impact on evolution and climate, but despite our knowledge, we remain at risk, as the cosmos is filled with unexpected threats. For instance, in the 20th century, several close encounters with asteroids occurred, and although they did not result in catastrophes, they demonstrated how close we are to becoming victims of a cosmic impact. Understanding these processes allows us not only to recognize the risks, but also to focus on possible precautionary measures that could help humanity avoid the consequences of such disasters. Scientific research continues, and for now, we can only observe the sky, hoping that our planet remains safe. When a celestial body, such as an asteroid or comet, enters Earth's atmosphere, its speed can reach from 10 to 100 kilometers per second. Upon entering the dense layers of the atmosphere, it experiences immense resistance, leading to significant heating of the object's surface. The temperature can rise to several thousand degrees Celsius, causing a bright glow and evaporation of the outer layers. Upon reaching Earth's surface, the body collides with it, releasing colossal energy equivalent to the explosion of several megatons of TNT. This energy creates a shock wave that spreads at incredible speed, destroying everything in its path. The shock wave compresses the air, creating a high-pressure zone that results in a loud sound reminiscent of a powerful explosion. During the collision, molten material is ejected, scattering over a radius of several kilometers. For example, when a meteorite fell into the Mexican Gulf around 65 million years ago, the ejector reached heights of 30 kilometers. The formation of a crater occurs due to the energy of the impact creating a central uplift, known as a central dome, as a result of the collapse of the upper layers of the rock after the impact. Craters can be enormous in size. The Chicxulub crater, formed by the impact of an asteroid, is approximately 180 kilometers in diameter. Seismic waves generated by such collisions spread across the planet, causing earthquakes and tremors that can be felt hundreds or even thousands of kilometers from the impact site. Studies show that these waves can cause significant damage in remote regions where there was no direct contact with the impact. For example, during this event in Mexico, seismic waves were recorded in North America and even in Europe. These vibrations can affect tectonic plates, triggering additional earthquakes. After the impact, the cooling and solidification of the ejected material begins, which later forms new geological structures. Therefore, the mechanisms of impact crater formation and the consequences of the impact of celestial bodies on Earth remain important topics for study in the field of planetary science. The application of these research findings can help understand not only the past, but also predict potential threats for the future. For example, the Vredefort crater in Russia, formed around 100 million years ago, serves as a clear example for studying the consequences of such catastrophes. Chicxulub crater, located on the southeastern coast of Mexico in the state of Yucatan, has a diameter of approximately 30 kilometers and a depth of more than 1 kilometer. The age of the crater is about 65 million years, which corresponds to the time of the mass extinction that led to the disappearance of around 75% of all species on Earth, including dinosaurs. This catastrophic impact occurred at the end of the Cretaceous period, when an asteroid larger than 10 kilometers in diameter struck the planet. The released energy was equivalent to billions of atomic bombs, causing massive changes in the climate and ecosystems of Earth. The crater was discovered in 1969 through geophysical research, and it was not until the 1990s that scientists began to realize its importance for understanding dinosaurs and their extinction. Geologists such as Dr. Alan Hilder from the University of California, Berkeley, conducted numerous studies in this area, collecting rock samples and studying the structure of the crater. It was found that the shock wave created powerful seismic waves that scattered debris over hundreds of kilometers. These debris, which contain high levels of iridium, indicate an extraterrestrial origin of the impact. Chicxulub crater has become an important object for study not only in geology but also in biology, as it symbolizes how cosmic events can influence the evolution of life on the planet. The size of the crater is impressive. It is surrounded by a rim up to 300 meters high, formed by the ejected material from the impact. On its floor, there are layers containing traces of a catastrophic fire and changes in ecosystems that occurred after the impact. These processes led to mass extinctions and changed the biological landscape of Earth, opening the way for new forms of life. Research on the crater continues to this day, attracting the attention of scientists from around the world who want to uncover the mysteries hidden within its depths. Scientists from the Mexican Institute of Astrophysics conduct analyses and modeling of the impact's consequences to understand how this event could have influenced climate changes and various biological adaptations. Chicxulub crater is not only a geological formation, but also a historical milestone that opened a new era in evolutionary biology. Significant findings such as meteorite fragments and fossil remains found near the crater help to reconstruct the picture of the catastrophe and its consequences. Moreover, the study of the crater allows scientists to better understand the possibility of similar catastrophes in the future, making it significant not only for historians, but also for planetary scientists. An asteroid that collided with Earth approximately 60 million years ago and created the Chicxulub crater had a diameter of about 10 kilometers and was moving at a speed of around 20 kilometers per second. This collision occurred at the end of the Cretaceous period, approximately 65 million years ago, and had catastrophic consequences for life on the planet. When the asteroid struck the surface, it released colossal energy, equivalent to more than 1 billion atomic bombs dropped on Hiroshima, resulting in an instantaneous flash of light that was hundreds of times brighter than the sun. This flash incinerated everything in its path, vaporizing rocks and ejecting massive clouds of dust and gas into the atmosphere, leading to the formation of a crater with a diameter of about 130 kilometers. Immediately after the impact, a shock wave was created, spreading at the speed of sound and causing powerful earthquakes. Subsequently, the release of a large amount of material into the atmosphere led to a global winter catastrophe, as sunlight was blocked, radically altering Earth's climate. Approximately 30% of the ejected material reached heights of 100 kilometers, and some fragments even escaped the atmosphere and entered space. This catastrophe resulted in mass extinctions, including dinosaurs, and fundamentally changed Earth's ecosystems. For millions of years, the traces of this collision have been preserved in the geological layer, studied by scientists to understand not only the consequences of the impact, but also its influence on the evolution of life on Earth. The Chicxulub crater has become an object of scientific interest, and its study continues as it provides unique data on catastrophic events that could occur in the future. The impact of an asteroid in Chicxulub caused a series of catastrophic events that transformed the planet in just a few hours. At the moment of collision, a powerful fireball was formed, releasing energy equivalent to millions of atomic bombs. The temperature on Earth's surface rose to 1,000 degrees Celsius, leading to the formation of fiery storms. These storms, covering vast areas, burned everything in their path, destroying forests and wildlife that could have survived in this hell. Simultaneously, the most powerful earthquakes began. The strength of these seismic waves reached 10 on the Richter scale, destroying mountain ranges and causing numerous landslides. The Earth shook so violently that entire continents shifted, disrupting ecosystems that had existed for millions of years. Lakes and rivers overflowed, resulting in massive tsunamis up to 100 meters high that crashed onto coastlines, wiping out everything in their path. These were waves that could have destroyed entire cities, leaving no trace. Following the tsunamis, the sky turned black from dust and smoke released into the atmosphere. As a result, acid rain began, containing sulfuric and carbonic acids. This rain killed plants and animals, exacerbating the ecological catastrophe. Scientists studying this era believe that the combination of these factors led to the mass extinction of species. Birds could not fly as the absence of sunlight and the sudden change in temperature made life impossible. Many species, including dinosaurs, could not adapt to the new conditions. The environment that had supported life for millions of years collapsed in an instant. More than 70% of all animal and plant species disappeared in a short period. This catastrophic day marked the beginning of a new era for Earth, where survival depended on the ability to adapt to completely new conditions. Ecosystems that had once been stable and diverse collapsed, leaving space for the development of new life forms that later became dominant on the planet. Scientific research shows that such events can happen again, and humanity must be prepared for such challenges. The impact of Chicxulub, which occurred around 65 million years ago, not only caused an instantaneous catastrophe, but also had long-term consequences that significantly altered the appearance of Earth. Dust and debris ejected into the atmosphere. As a result of the impact created what is known as the impact winter. Due to this phenomenon, sunlight could not reach the planet's surface, leading to a sharp drop in temperature. Research indicates that the temperature could have fallen by tens of degrees Celsius over several months, and in some areas even by 30 degrees. Photosynthesis, a vital process for plants, practically ceased, triggering the collapse of ecosystems. Without sunlight, vegetation began to die off, and food chains on which many animal species depended collapsed. Birds, reptiles, and mammals that could have survived these conditions became victims of food scarcity. Scientists believe that as a result of this mass extinction, around 70% of all species on Earth disappeared. In particular, dinosaurs, which had dominated the planet for over 160 million years, vanished almost overnight. Studies conducted by geologists show that during this period, a mass extinction known as the Cretaceous-Paleogene boundary occurred, which altered the biosphere for millions of years to come. Examining sedimentary rocks, scientists found high levels of iridium, a rare element typically found in meteorites, which confirmed the hypothesis of the cosmic origin of the catastrophe. Meanwhile, in the oceans, the oxygen level also began to decline, initiating another wave of extinctions among marine organisms. This process underscores how global catastrophes can trigger chain reactions in ecosystems, leading to changes that persist for centuries. As a result of these changes, ecosystems that were stable and diverse transformed, giving way to new forms of life such as mammals, which were able to occupy niches left vacant by the mass extinction. These new species adapted to the changed conditions, ultimately leading to the evolution of modern mammals, including humans. This transitional period spanned millions of years, during which life on Earth was restored, but in a completely new form. Scientific research conducted in recent decades shows that such catastrophes could recur in the future, and humanity must be prepared for new challenges in climate change and ecosystem transformation. 66 million years ago, the Chicxulub impact event was a catastrophic occurrence that marked the end of the era of dinosaurs, which had dominated Earth for over 150 million years. This asteroid, with a diameter of approximately 10 kilometers, struck the territory of present-day Mexico, creating a crater about 130 kilometers in diameter. The impact generated powerful seismic waves and ejected a vast amount of dust and debris into the atmosphere, leading to a sharp decrease in sunlight and significant climate changes. The planet's temperature dropped and a global nuclear winter began, which destroyed vegetation and, consequently, food chains. As a result, dinosaurs, once the rulers of the land, found themselves in conditions where their usual adaptations no longer worked. For instance, large herbivores like Triceratops and Brontosaurus were unable to find enough food because the forests and grasslands they grazed on were destroyed. Meanwhile, carnivorous dinosaurs like Tyrannosaurus rex found themselves at a disadvantage because their prey had disappeared. Models of extinction show that more than 90% of all dinosaur species went extinct as a result of this cataclysm. At the same time, some small mammals and reptiles with high reproductive rates and adaptive abilities managed to survive and occupy the ecological niches left vacant. This extinction, in essence, paved the way for new forms of life, including mammals, which over time evolved into modern humans. This event was a turning point in Earth's history, altering the course of evolution forever. The exact timing and conditions of this impact are still being studied by scientists and remain a subject of active research. For example, in 2005, an international group of scientists confirmed that this impact was the catalyst for the mass extinction, using data from geological layers found in different parts of the world. The study of fossils and fossilized remains shows that even the most powerful and adapted species could not cope with such abrupt climate changes. This catastrophe was one of the most significant in Earth's history and clearly demonstrates how rapidly living conditions can change and how even the greatest creatures can disappear from the face of the Earth. After the Paleocene-Eocene extinction event, which occurred around 66 million years ago, only small mammals, some bird species, crocodiles and turtles survived. Small mammals, such as the ancestors of modern rodents and insectivores, were able to adapt due to their small size and high reproductive capacity. They could hide in burrows and crevices, sheltering from predators and unfavorable conditions that prevailed on the surface. Scientists believe that these adaptations allowed them to survive in a world where many large species had gone extinct. Over time, these mammals began to actively occupy the ecological niches that had been vacated, which became the basis for their radiation in subsequent epochs. Birds also became important survivors after the catastrophe. They possessed unique adaptations such as lightweight bones and feathers, which allowed them not only to fly, but also to quickly move in search of food. Some bird species, such as the ancestors of modern parrots and sparrows, began to actively use seeds and fruits as a food source, giving them a significant advantage in the changing landscape. Evidence shows that by the end of the Paleocene, bird diversity increased, and they began to occupy a variety of ecological niches, from terrestrial to arboreal. Crocodiles, as resilient predators, also survived this extinction. Their ability to adapt to various environmental conditions, including both freshwater and saltwater, made them competitive in various ecosystems. By the time a new era began, crocodiles had taken on important roles in their ecosystems, and their morphology allowed them to survive in conditions where other species could not adapt. For example, their powerful jaws and ability to go without food for long periods were crucial for their survival. Turtles, on the other hand, developed hard shells that protected them from predators. These reptiles could survive in conditions of food scarcity by slowing their metabolism and using fat reserves. Their long-lived individuals also managed to survive in conditions of ecosystem instability, allowing turtles to begin colonizing new territories. By the time the Paleogene began, turtles began to actively spread, filling new ecological niches that had been created after the disappearance of large species. These groups of organisms became the main players in the new ecosystems that emerged after the extinction. Small mammals, birds, crocodiles, and turtles not only survived but also began to actively develop and adapt to new conditions, leading to diversity and evolutionary changes that we observe today. As a result of all this, new species of mammals, including the ancestors of modern mammals, emerged and began to fill the ecological niches previously occupied by dinosaurs. By the end of the Paleogene, there was a radical change in the structure of ecosystems, which became the basis for further development of life on Earth. Supervolcanoes are among the most powerful geological structures on the planet, capable of ejecting immense volumes of magma and volcanic gases into the atmosphere. Unlike ordinary volcanoes, which typically expel tens of cubic kilometers of material in a single eruption, supervolcanoes can release hundreds and sometimes thousands of cubic kilometers. These colossal volumes make them potentially catastrophic for global climate and ecosystems. Supervolcanoes form as a result of the accumulation of magma in large reservoirs beneath the Earth's crust, leading to the creation of enormous calderas that can reach tens of kilometers in diameter. For example, an eruption of a supervolcano can occur when the pressure of the magma becomes so great that the Earth's crust cannot contain it, resulting in an explosion that can devastate the surrounding area and eject ash into the atmosphere, causing global climate changes. During an eruption, supervolcanoes release not only magma and ash, but also significant volumes of sulfuric gases, which can lead to the formation of acid rain. The temperature on the planet can drop by several degrees, which in turn can have serious consequences for agriculture and ecosystems. The study of supervolcanoes has become particularly relevant in light of contemporary climate changes. Scientists are conducting active research to understand how such catastrophes can affect the global environment. For instance, scientists from the University of California, Berkeley, have modeled the possible consequences of a supervolcano eruption, demonstrating that even a small eruption can cause significant climate changes. It is important to note that supervolcanoes can remain active for millions of years, and their potential eruption can have consequences not only for nearby regions, but for the entire planet. One of the most famous examples of supervolcanoes is Yellowstone, which has been erupting massive volumes of magma for millions of years, leaving behind impressive geological formations. Supervolcanoes can also influence the lives of animals and plants, destroying familiar ecosystems and creating new conditions for survival. They become a sort of laboratory for studying the process of evolution and adaptation of species to extreme conditions. Research shows that after large eruptions, recovering ecosystems can look completely different from before the catastrophe, highlighting the significance of supervolcanoes as factors shaping the biosphere. There is also the view that supervolcanoes can cause mass extinctions of species, which is confirmed by the findings in geological layers where traces of volcanic activity have been discovered. Supervolcanoes not only pose a threat to humanity, but are also important objects of scientific research that help us better understand how our planet functions and which processes can lead to global changes. It is important that modern monitoring methods allow scientists to track the activity of supervolcanoes, giving them the opportunity to predict possible eruptions and minimize the consequences for the population. Supervolcanoes remain one of the most mysterious and dangerous geological formations, requiring constant attention and study. Their impact on climate, ecosystems, and the evolution of species makes them important objects for understanding the geological history of Earth and its future. Thus, supervolcanoes represent not only the power of nature, but also a significant aspect of the study of the interaction between humans and their environment. Their study helps to reveal the mysteries not only of the distant past, but also to predict possible scenarios for the future. Supervolcanoes can eject up to 1,000 cubic kilometers of material in a single eruption. Yellowstone caldera is an impressive geological formation that resulted from powerful volcanic eruptions, the first of which occurred approximately 240,000 years ago. It has a diameter of about 30 kilometers and covers an area of more than 80 kilometers in length. The structure of the caldera includes numerous geothermal features such as geysers, hot springs, and mud volcanoes, making it a unique place on the planet. For example, the famous geyser Old Faithful ejects water up to 30 meters high every 80 minutes, demonstrating the activity of magma beneath the surface. This magma is contained in a reservoir estimated to be more than 600 cubic kilometers in volume, which is several times larger than the volume of the caldera itself. Beneath this picturesque landscape lies the power capable of causing catastrophic changes on the planet. Volcanologists note that the caldera exhibits signs of activity, such as small earthquakes and ground uplifts, which are detected using seismographs. Research conducted in 2006 using satellite data showed that in some areas of the caldera, the surface is rising by several centimeters per year. This indicates that magma continues to accumulate and the potential threat of an eruption remains relevant. The volcanic activity of Yellowstone is sustained by geothermal gradients that can reach 100 degrees Celsius per 100 meters of depth. In this context, it is important to note that the caldera is not only a beautiful place with scenic landscapes, but also a potential source of catastrophic natural phenomena that can affect not only the climate in the United States, but also around the world. Each geyser and hot spring is just a small manifestation of what lies beneath the surface, where a vast amount of energy awaits its moment. Volcanologists continue to monitor the activity of the caldera using modern technologies to analyze changes occurring in it. In 2009, a monitoring program was launched that includes GPS and other high-precision instruments, allowing even the smallest geological changes in the region to be detected. Interestingly, on the territory of Yellowstone National Park, samples of lava dating back several million years have been found, which confirms the long history of volcanic activity in this region. The presence of such ancient samples indicates that the caldera is not only active today, but has played a significant role in shaping the surrounding landscape over millions of years. The volcanic nature of Yellowstone makes it not only an object of scientific interest, but also a place where a person can feel the power of nature in its pristine form. The last major eruption of Yellowstone volcano occurred approximately 600,000 years ago and was one of the most powerful volcanic events in Earth's history. This eruption resulted in the formation of a vast caldera with a diameter of more than 30 kilometers. The volume of the volcanic material ejected is staggering. Scientists estimate it at more than 1,000 cubic kilometers of ash and lava. The ash, released into the atmosphere, spread over thousands of kilometers, obscuring the sky over North America and even reaching distant regions such as the eastern states of the USA and parts of Canada. As a result of this catastrophic event, there was a sharp change in climate that lasted for several years. Sunlight barely pierced through the ash clouds, leading to a significant drop in temperature, sometimes by as much as 10 degrees Celsius. This cold period, known as the volcanic winter, caused massive die-offs of vegetation, as plants were covered in a layer of volcanic material that deprived them of sunlight and the resources needed for photosynthesis. Scientists note that such consequences could have had long-term impacts on ecosystems, as the changing climate disrupted the usual growth and development cycles. The study of this eruption and its aftermath continues, as it serves as a clear example of how volcanic activity can alter not only local, but also global climate. As a result, ecosystems that were under threat began to recover only decades, if not centuries, after the eruption, which underscores the immense scale of the impact of volcanoes on planetary processes. Supervolcano Toba is located on Sumatra, Indonesia, and is one of the largest calderas in the world, formed as a result of one of the most powerful eruptions in Earth's history, which occurred approximately 74,000 years ago. The diameter of the caldera is approximately 125 kilometers, and in some places the depth reaches more than 400 meters. This eruption, known as the Toba event, released a vast amount of ash and volcanic gases, which, according to scientists, led to global cooling and possibly a reduction in the human population to a few thousand individuals. Within the caldera, Lake Toba formed, which is the largest volcanic lake in the world, with an area of around 1,100 square kilometers and a maximum depth of 500 meters. The landscape around the lake is breathtaking. Clear blue water is surrounded by green hills and picturesque islands, such as Sumatra and Sipora, creating an ideal place for relaxation and nature observation. While Lake Toba appears serene and attracts tourists to its shores, beneath it lies a tremendous potential for destruction. Geologists continue to study Toba's activity as the volcanic system in this region remains seismically active. For example, in 2012, several small earthquakes occurred, serving as a reminder of nature's power. This volcanic region is also characterized by a unique ecosystem, including rare plant and animal species that have adapted to the specific conditions associated with volcanic activity. Scientific research shows that Toba's eruptions have occurred multiple times over the past millions of years, each significantly altering the local landscape. The recovery of the ecosystem around Lake Toba after the last major eruption took thousands of years, highlighting the magnitude of this event. Researchers like Dr. Benjamin Brook from the University of Pennsylvania study volcanic ash deposits to understand how climate conditions changed in response to such catastrophic events. This work provides insights not only into Toba's history, but also into global climate changes over the past millennia. Toba's volcanic activity remains a subject of intense study, as it may offer clues about how other supervolcanoes could influence future climate. Lake Toba and its surroundings not only attract tourists but also serve as a significant site for scientific research that can help predict possible changes in climate and ecosystems on our planet. Toba remains a living reminder of how powerful natural forces can shape not only the landscape but also the fate of humanity. The eruption of Toba occurred around 74,000 years ago and was the most powerful volcanic event in known human history. This eruption released approximately 1,000 cubic kilometers of ash and volcanic gases into the atmosphere, leading to global climate changes. The ash rose to heights of more than 30 kilometers, enveloping the sky and blocking sunlight for many years. This darkness caused a sharp cooling, known as the volcanic winter, which lowered the climate by several degrees. Studies indicate that temperatures may have dropped by 8 degrees Celsius in some regions of the world, resulting in widespread crop failures and famine. As a result of this catastrophe, the population of early humans is estimated to have declined to a few thousand individuals. Scientists like Professor Klaus Hasselmann assert that this event could have been one of the factors contributing to the development of modern Homo sapiens, as survival in resource-scarce conditions required adaptation and evolution. Evidence of this catastrophic eruption has been found in various geological layers, including ash deposits in places like the Indian Ocean and Southeast Asian islands. Volcanic gases such as sulfur dioxide contributed to the formation of sulfuric acid in the atmosphere, leading to acid rain and further exacerbating living conditions. There are theories that this eruption may have also influenced human migration routes, forcing groups to move in search of more favorable conditions. It took many thousands of years for ecosystems to recover, and the restoration of flora and fauna required millennia. Scientific research, such as the work of a group of geologists led by Dr. John Watt, shows that such volcanic catastrophes can have long-term consequences for the climate of Earth and its inhabitants, altering ecological niches and forcing species to adapt to new conditions. The Toba volcano is not just a geological phenomenon. It is a symbol of the power of nature capable of altering the course of human history. As shown by paleogenetics data, the genetic diversity of the modern human population was significantly reduced as a result of this eruption, which may have affected our evolutionary path. The scale of this event cannot be underestimated. It was one of the most significant catastrophes in human history, and its effects were felt for tens of thousands of years. Volcanic deposits found on islands like Sumatra contain layers that confirm the magnitude of the eruption and its impact on ecosystems. The Toba volcano continues to be a focus of attention not only for scientists, but also for historians trying to understand how this event shaped human civilization, as well as for climatologists studying the impact of volcanic activity on the modern climate. Volcanic activity is a powerful factor that significantly influences Earth's climate. During eruptions, volcanoes release large amounts of gases into the atmosphere, such as sulfur dioxide, carbon dioxide, and water vapor, as well as aerosols consisting of small particles of ash and soot. These substances can substantially alter the transparency of the atmosphere, creating clouds that reflect solar radiation back into space. For example, sulfur dioxide, when it enters the atmosphere, condenses into sulfuric acid droplets, forming aerosol clouds that can reduce the amount of solar radiation reaching Earth's surface. Studies show that such changes can cause temporary cooling of the climate over several years, affecting agriculture, ecosystems, and even ocean levels. On the other hand, carbon dioxide, which is also released during eruptions, contributes to the greenhouse effect. It traps heat in the atmosphere, and unlike the short-term effects of aerosols, its impact can last for decades or even centuries. As a result, volcanic activity creates complex interactions between short-term and long-term climate changes, making climate prediction challenging. Volcanologists and climatologists conduct active research to better understand how volcanic gases and aerosols interact with Earth's climate system. For instance, a model developed in the 12th decade of the 21st century shows that even slight changes in volcanic activity can cause significant temperature fluctuations on the planet. It is important to note that this process does not occur in isolation. The interaction of volcanic emissions with other climate factors, such as solar activity and ocean currents, adds additional layers of complexity. Volcanic eruptions can also affect rainfall patterns, altering water cycles. In some cases, these changes can lead to droughts in certain regions and floods in others, particularly in tropical and subtropical zones. Therefore, volcanic activity is an integral part of a broader climate system where internal Earth processes have a noticeable impact on atmospheric phenomena. Current research indicates that over the past century, the level of carbon dioxide in the atmosphere has increased by more than 30%, which is also linked to human activity, but volcanic activity remains a significant natural factor influencing climate fluctuations. Volcanic gases and aerosols can remain in the atmosphere for several days to several years, depending on the magnitude of the eruption and the height to which they rise. These processes highlight the importance of studying volcanic activity as a key element in understanding climate changes. In the 18th year of the 19th century, the world encountered an extraordinary climatic phenomenon known as the Year Without a Summer. This anomalous event was caused by the catastrophic eruption of the Tambora volcano on the Indonesian island of Sumbawa in April 1816. This eruption, one of the most powerful in history, released a massive amount of ash and volcanic gases into the atmosphere, leading to a significant drop in global temperature. The summer of 1816 was not just cold, but exceptionally so. In Europe, according to meteorological observations, the temperature dropped by 8 degrees Celsius compared to normal summer levels. In some regions, such as New England in the United States, snow fell in June, causing bewilderment and fear among the local population. People went out onto the streets in winter coats, looking at the snow-covered landscapes that should have been green and blooming. Agriculture, the backbone of the economy at the time, suffered catastrophic losses. The grain crops sown in the spring could not ripen due to the cold air and constant rains, destroying the harvest. In New England, where in normal years enough wheat was harvested to feed the population, in 1816 there was a complete failure. Farmers could not even gather half of their usual harvest, leading to a famine. The situation in Europe was no better. In Germany, France, and Britain, there were widespread crop failures and food prices skyrocketed. People began to panic, and in some areas there were uprisings against the high bread prices. In Switzerland, for example, local residents gathered in cities, demanding action from the authorities to combat the famine. the uncertain climatic conditions caused alarm, and some even believed it to be a harbinger of the end of the world. At that time, the scientific community did not have a sufficient understanding of the connection between volcanic activity and climate change. Although some scientists, such as the English naturalist Joseph Banks, began to suggest that volcanoes could influence the climate, most people remained unaware. As a result of the year without a summer, hundreds of thousands of people faced famine, poverty, and despair. This climatic catastrophe became one of the first examples of how natural phenomena can have a profound impact on human life and society as a whole. In 1816 in New England, according to data, at least 30% of the population suffered from food shortages. While some sought explanations in religion and superstitions, others began to realize the need for a scientific approach to studying nature. Nevertheless, this strange and ominous year left a deep impression on people, making them reflect on how fragile human civilization is in the face of the power of nature. The 18th year of the 19th century served as a kind of lesson, a reminder that the climate can change and that humanity must be prepared for the unexpected. The year without a summer, the 18th year of the 19th century, had a profound impact on the cultural life of Europe, inspiring numerous artists and writers to create dark and ominous works. During this time, Mary Shelley, while in Switzerland with Percy Shelley and Lord Byron, wrote her famous novel Frankenstein. It is interesting to note that the unfavorable climatic conditions caused by the eruption of the Tambora volcano in 1816 served as a catalyst for the creation of this Gothic tale. Shelley depicted her monster as a symbol of fear that humanity might create something that would escape their control. This reflects not only the personal fears of the authors, but also the general state of society in the face of natural disasters. Artists of the time, such as Caspar David Friedrich, also transferred their gloomy moods to canvas. In his works, one often finds desolate landscapes with solitary figures, emphasizing a sense of loss and despair. For example, the painting The Wanderer Above the Sea of Fog shows a person standing on the edge of a cliff, gazing at the vast foggy expanse, symbolizing the internal struggles that plagued people during this dark period. Literature of the time also reflected apocalyptic sentiments. Works such as Melmoth the Wanderer by Edgar Allan Poe conveyed a sense of hopelessness and fear of the future. Inspired by natural disasters, authors created images filled with chaos and destruction, which became iconic of this period. William Blake, a poet and artist, also emphasized the conflict between humanity and nature, depicting nature as an uncontrollable force capable of destroying human achievements. One of Blake's notable works is The Ancient of Days, where he portrays the struggle for salvation in the face of a natural catastrophe. This state of society and art became a reflection of the fear and anxiety that prevailed in the face of natural disasters. As a result, the consequences of the year without a summer not only shaped cultural trends, but also left a legacy in the form of works that have become classics, including the novel Frankenstein, which continues to be relevant in discussions about scientific experiments and their consequences. The 18th year of the 19th century marked a turning point in the history of art and literature, creating a unique cultural context that continues to influence contemporary perceptions of nature and human civilization. Glacial periods represent cycles during which vast masses of ice cover significant portions of continents, altering the landscape and climate of Earth. These cycles are characterized by the alternation of phases of glacial advance and retreat, which result in profound changes in ecosystems and geographical forms. Glaciers, moving southward, engulf everything in their path. They carve valleys, form lakes, and alter river courses. For example, glaciers that once covered North America left behind characteristic traces, such as the Great Lakes, which were formed when ice masses carved out extensive depressions in the Earth's crust. This process is slow but inexorable. Over thousands of years, ice can advance tens of kilometers, and then, in response to climate change, retreat, leaving behind a transformed landscape. This natural phenomenon also affects sea level and the distribution of precipitation. During glacial periods, sea level decreases because a significant portion of water freezes, and when the ice retreats, sea level rises, which in turn alters coastal ecosystems. Glaciers, like giant sculptors, create new forms of relief. They form moraines, boulders, and other geological formations that bear witness to their power. Important roles in this process are played by climatic conditions, which can promote both glacial advance and retreat. For instance, a change in temperature by a few degrees can have catastrophic consequences. If the temperature rises, ice begins to melt, and the rate of this melting can significantly increase, leading to further changes in ecosystems. Scientific research shows that over the past 2 million years, Earth has experienced at least 5 major glacial periods, each of which has left its mark on the planet. Studying these cycles allows scientists to understand how glacial processes influence climate and the environment. Scientists have used radiocarbon dating methods to determine the age of samples found in ice layers and to identify cycles that occurred in the past. These studies show that glacial periods have significant importance in shaping the modern world. Glaciers, despite their massiveness and apparent immobility, are constantly in motion, their fluidity and strength capable of transforming entire ecosystems and creating new conditions for life. There are also historical records of how glacial periods influence the emergence and development of human civilizations. Climate change caused by glacial retreat could have facilitated human and animal migrations, which in turn influenced the spread of cultures and technologies. For example, many researchers link the transition of humanity to a settled lifestyle with climate change following the end of one of the glacial periods, which led to the development of agriculture and urban civilizations. Glacial processes, therefore, not only shape our planet but also influence human history. Glacial research conducted by scientists worldwide helps to better understand the mechanisms governing our climate and predict the consequences of changes that may occur in the future. An important aspect is that processes related to glaciers continue to influence contemporary climatic conditions, and understanding these phenomena is necessary for adapting to the challenges they may bring. Scientific data indicate that the melting of glaciers due to global warming is occurring at an alarming rate, which could lead to a rise in sea level by several meters in the future. The last glacial maximum occurred around 20,000 years ago, when a significant portion of the northern hemisphere was covered by a thick layer of ice, reaching up to 3 kilometers in some places. This ice sheet extended from Scandinavia to North America, including the territories of modern Canada and northern US states. Glaciation led to a substantial decrease in sea level, which was approximately 100 meters lower than today, opening up new lands such as the Bering Land Bridge between Asia and North America, allowing animals and humans to migrate between continents. Climate zones changed, tundras and steppes replaced warm forests, creating harsh conditions for habitation. Various species of the glacial period, including mammoths, woolly rhinos, and giant sloths, inhabited these expanses. Mammoths, for example, reached heights of up to 4 meters and had long, curved tusks that they used to break through snow in search of food. These animals migrated across vast plains in search of pastures, while their predators, such as saber-toothed tigers and giant bears, hunted them. At a time when the level of carbon dioxide in the atmosphere was significantly lower than today, ice sheets maintained their massive coverage, creating cold and harsh conditions that influence climate and ecosystems worldwide. The glaciated zone extended for thousands of kilometers, and glaciers formed unique landscapes such as lakes and valleys that later became the basis for modern ecosystems. On the southern edge of the glaciers, where the climate was milder, Arctic tundras formed, inhabited by mosses and lichens that served as food sources for various herbivores. In these conditions, survival was a real challenge. Only the most adapted species could withstand the harsh winters and food scarcity. The glacial maximum not only altered the geography of the planet, but also had a significant impact on human migration. Hunter-gatherers began to move to new regions in search of resources, marking the beginning of their spread across Europe and Asia. Scientific research shows that these migrations were linked to changes in the environment when available resources became increasingly limited. Eventually, around 10,000 years ago, glaciers began to retreat, opening up new territories for human and animal settlement, marking the transition to the Neolithic era and the beginning of the agricultural revolution. As a result, the last glacial period can be considered a crucial stage in human history, shaping not only nature but also the fates of people. While glaciers retreated, sea level began to rise again, flooding previously exposed lands and changing the migration routes and ways of life of various cultures. During the last ice age, which lasted approximately from 100,000 to 10,000 years ago, the Earth was home to an extraordinary megafauna, including giants such as mammoths, woolly rhinos, cave bears, and saber-toothed cats. Mammoths, majestic creatures, could reach heights of 4 meters and weigh up to 6 tons. Their enormous tusks, up to 5 meters long, were used not only for defense against predators, but also for digging through snow in search of food. These herbivores inhabited cold tundras and steppes of Eurasia and North America, where their herds formed complex ecosystems, supporting a variety of plant life. Woolly rhinos, with their thick and long fur, were adapted to harsh climatic conditions, and their sizes, reaching up to 2 meters in height, made them some of the largest herbivores of their time. They fed on grasses and shrubs, leaving characteristic traces on the landscapes of the Ice Age plains. Cave bears, standing up to 2.5 meters tall, were among the largest bear species ever to exist on the planet. Their powerful jaws and large teeth allowed them to hunt large animals and catch fish. These bears used caves as shelters where they hibernated during the winter, enabling them to survive in the harsh climate. Saber-toothed cats, with their characteristic long canines that could reach up to 25 centimeters, became formidable predators in this world. They hunted large herbivores such as mammoths and woolly rhinos, using their speed and agility to catch prey in open landscapes. These cats could weigh up to 130 kilograms and reach lengths of up to 3 meters, making them some of the most dangerous predators of their time. The harsh climate of the last ice age contributed to the formation of unique ecosystems, where giant herbivores supported plant life and predators adapted to hunting in open landscapes. For example, mammoths and rhinos created pastures that promoted the growth of various types of grasses and shrubs, thus providing food for other animals. It is interesting to note that the study of the remains of these animals shows that during hunts on mammoths, saber-toothed cats used cooperation and group hunting strategies, which allowed them to more effectively capture large prey. It is important to note that the last representatives of the megafauna went extinct approximately 10,000 years ago, likely due to a combination of climate changes and hunting by early humans. These changes in ecosystems opened up new niches for other species, but left behind an unparalleled legacy in the form of fossils and artistic depictions found in caves, which testify to life in this harsh but vibrant world. As a result, the study of the megafauna of the last ice age allows us to understand how climatic conditions and ecological interactions shape life on our planet. Remains of mammoths have been found in places like Siberia, where they have been preserved in permafrost and their tusks have become a target for humans who use them to make tools and works of art. At the end of the Pleistocene epoch, approximately 11,000 years ago, there was a significant melting of glaciers, which opened up vast territories that had previously been covered by ice. This event was a result of global warming, caused by changes in solar radiation and an increase in the concentration of carbon dioxide in the atmosphere. Glaciers that once stretched from Canada to Scandinavia began to retreat rapidly, freeing up extensive areas of land. In the places of the ancient glaciers, new lakes formed, such as Lake Michigan and Lake Superior, creating complex river systems that began to develop actively. These water bodies became a source of life for numerous flora and fauna species that had not previously been able to inhabit these regions. With the retreat of the ice, ecosystems underwent significant changes. Initially, grasslands emerged on the liberated territories, followed by forests gradually advancing northward, replacing tundra and taiga. Initially, these were low-growing shrubs and grasses that diversified over time and gave way to coniferous forests, such as pines and spruces. Over the course of thousands of years, forests continued to expand, creating new ecosystems that became home to animals like deer, bears, and wolves. Around 8,000 years ago, the formation of mixed forests began, where pines coexisted with deciduous trees such as oaks and beeches. This process was not just natural, but also depended on various factors such as climatic conditions, soil types, and interactions between species. The level of the world ocean began to gradually rise, resulting in some coastal territories being submerged. For example, bays like Chesapeake and California began to form due to this rise in sea level. It is important to note that the melting of glaciers also led to changes in climate in other regions, contributing to more humid conditions in some places and droughts in others. This created diverse microecosystems, which contributed to biological diversity. As a result, by 7,000 years ago, forests had occupied significant areas, and the diversity of species continued to grow, with ecosystems becoming increasingly complex. Ultimately, this process contributed to the formation of the modern ecosystems that we can observe today. During the melting of glaciers, especially during rapid warming, catastrophic floods occurred due to the breach of glacial lakes. These lakes formed when glaciers held back water, creating temporary reservoirs that could reach significant sizes. One of the most famous examples is Missoula Lake in the United States, which existed around 20,000 years ago. When the glacier that held this lake began to melt, a breach occurred, and water rushed out with immense force. Megafloods caused by this event shaped valleys and canyons that can still be observed today. In a matter of days or even hours, this powerful mass of water eroded rock, creating a specific landscape known as iskabland. This term encompasses complex systems of deposits and erosion features left behind by such catastrophic events. For instance, the breach of Missoula Lake resulted in water flows reaching speeds of up to 11 meters per second, allowing them to erode sedimentary rocks and create deep canyons like Grand Coulee, which is now one of the most impressive geological formations on the planet. Occasionally, when the water level in lakes reached critical levels, catastrophic breaches occurred, causing floods that could cover hundreds of square kilometers. These water flows created new river channels, altered landscapes, and formed new ecosystems that later adapted to the conditions created by the powerful floods. The force of these water flows was so great that they could move massive rocks weighing several tons, leaving them in new locations, clearly demonstrating the power of nature. As a result of such events, such as the breaching of glacial lakes, diverse geological structures were formed that are now objects of study for geologists and historians. For example, in Scotland, after the melting of glaciers, extensive terraces were formed, which now serve not only as natural landmarks but also as important archaeological sites where traces of ancient civilizations are found. Such phenomena not only changed the appearance of the landscape but also influenced climatic conditions, creating new ecosystems that subsequently developed in accordance with changing conditions. In some regions where such floods occurred, scientists have found evidence that they contributed to the migration of people and animals, as the altered landscapes provided new opportunities for hunting and resource gathering. The powerful water flows left behind traces that can be detected even after millions of years, making the study of these events particularly important for understanding the history of the Earth. The disappearance of megafauna at the end of the Pleistocene was one of the most significant ecological catastrophes in Earth's history, occurring approximately between 12 and 10,000 years ago. During this period, the planet was inhabited by giant creatures such as mammoths, mastodons, giant sloths, and saber-toothed tigers, which formed unique ecosystems adapted to the harsh conditions of the Ice Age. For example, mammoths could reach heights of up to 4 meters and weigh up to 6 tons, allowing them to survive in the cold climate of the tundra. Their milk teeth had special structures that enabled them to digest tough grass and shrubs, making them an essential part of the ecosystem. However, with the onset of warming and the rapid changes in climate, the living conditions of these large mammals began to deteriorate. The climatic changes of this time led to a significant reduction in ice caps and an increase in the forested areas previously occupied by tundra. This reduction in open spaces necessary for pastures created serious problems for the survival of mammoths. Research conducted by scientists from the Institute of Evolutionary Biology in St. Petersburg shows that an increase in temperature by 3 to 4 degrees Celsius resulted in changes in the vegetation cover, which in turn disrupted the food chain on which these giants depended. In addition to climatic changes, human activity also contributed to the extinction of megafauna. The first Homo sapiens began to actively migrate around the world, hunting large animals. Archaeological excavations conducted in North America show that people used complex tools such as spears for hunting mammoths and mastodons. Calculations by archaeologists indicate that a group of hunters could kill up to 10 mammoths in one evening, creating a significant burden on the population. Around 13,000 years ago, hunters would often leave behind the bones and remains of animals, which were later analyzed by scientists, establishing a link between hunting and the decline in the population of megafauna. Some researchers, such as Dr. Sean M. Hopper from the University of California, argue that human impact was not the sole cause. Their studies consider the concept of multiple factors interaction, where the combination of hunting and climatic changes led to lasting consequences. As a result, by the time the climate finally stabilized around 10,000 years ago, not only mammoths, but also other species such as giant sloths, which weighed up to 400 kilograms and could only move through trees, had become extinct. These changes in the ecosystem led to the loss of entire complexes of species that existed in symbiosis with each other and their environment. While some smaller species, such as bison and deer, were able to adapt to the new conditions, others disappeared without a trace, leaving behind only fossils that modern scientists continue to study. For example, DNA analysis of extinct species shows that mammoths had genetic mutations that helped them survive in cold conditions, but these adaptations became insufficient with the changing climate. Comparisons of data on the extinction of megafauna in different regions, such as Australia, where species like the marsupial lion and giant kangaroos disappeared, also confirm that the combination of climatic changes and human pressure was catastrophic for entire ecosystems. The disappearance of megafauna not only altered the landscape of Earth, but also influenced the development of human communities, which began to adapt to the new conditions, transitioning from hunting large animals to hunting smaller species and gathering. These changes, in a sense, served as a prelude to the agricultural revolution, which occurred later when people began to cultivate agriculture and livestock. Thus, the extinction of megafauna became not only an ecological catastrophe, but also a significant milestone in human history, determining the further development of civilization. Scientists continue to discover new fossils and artifacts that help better understand how the survival of humans and megafauna intersected during this critical period. Meteorite craters are traces of cosmic impacts that leave an indelible mark on the geological record of our planet. These craters form as a result of meteorite collisions with Earth, and each such impact, as a rule, has catastrophic consequences for the surrounding environment. Scientific research shows that over the past 4 billion years, millions of meteorites have struck Earth, leaving their mark, from small indentations to giant craters with diameters reaching tens of kilometers. For example, the Chicxulub crater in Mexico, which formed around 65 million years ago, is one of the largest and most famous, as its formation is linked to the mass extinction of dinosaurs. Scientists have discovered that these craters can be not only geological formations, but also important indicators of historical events on Earth. Using radiometric dating methods, such as the uranium lead method, researchers determine the age of craters and correlate them with other geological changes, allowing for a more comprehensive understanding of the state of the planet in different epochs. These craters serve as a kind of book, recording the stories of collisions and their consequences, enabling us to see how the forces of the cosmos interact with Earth. Each crater, like a page in this book, tells the story of a time when a meteorite entering the atmosphere burned air and caused enormous explosions, leading to colossal changes in ecosystems. Thus, meteorite craters are not just geological formations. They are reminders of how vulnerable Earth is to the forces of the cosmos. These interactions of cosmic objects with our planet continue today, and although most of them do not reach the surface, sometimes events occur that can have a significant impact on the biosphere. For example, 87,000 years ago, a meteorite impact on the territory of modern Arizona created the Barringer crater, with a diameter of about 1 kilometer. This crater is the result of an impact by a meteorite weighing around 30 tons, which entered the atmosphere at a speed of 20 kilometers per second. The traces of such events are preserved in sedimentary rock formations, making them important objects for study by both geologists and astronomers. They help understand not only the history of Earth, but also the general processes occurring in the solar system. For instance, craters on the Moon or Mars, studied by missions such as Apollo and Mars rover, indicate that similar impacts occurred on other celestial bodies, challenging the uniqueness of Earth's conditions. Craters serve not only as reminders of past catastrophes, but also as warnings of possible future threats, when powerful meteorites can cause global changes similar to those that occurred millions of years ago. Research on craters continues, and each discovery adds new information to our understanding of the world, where Earth is not the only arena for collisions and destructions. Meteorite craters also enrich our experience in studying other planets, as they can provide keys to understanding the processes that shape not only Earth, but the entire solar system. The Meteor crater, located in the state of Arizona, is a striking testament to the power of cosmic collisions that have occurred on Earth. This crater, also known as the Meteor crater, has a diameter of approximately 1 kilometer and a depth of around 120 meters. It was formed about 50,000 years ago as a result of an impact by a meteorite weighing around 27 tons, traveling at a speed of about 27,000 kilometers per hour. Visually, the crater is impressive. Its edges drop sharply into the depth, and its internal walls are covered with debris and rocks ejected during the impact. Standing at the edge of the crater, a person can feel the magnitude of this event, a giant wound on the surface of the Earth, resembling the trace of a massive impact left by an extraterrestrial body. This is not just a depression, but a whole ecosystem with diverse plants and animals that have adapted to the conditions created by this catastrophic event. The preservation of the crater is remarkable. Despite its age, it has been well preserved and has become an object of study for geologists and meteorite experts. Intensive research of the crater began in the early 20th century, when in 1930 the first scientific investigation was organized, headed by geologist and paleontologist Dr. Edward Charles. During the work, samples of the rock were collected, which helped scientists understand the composition of the meteorite and its impact on the surrounding environment. The crater has become not only an object of scientific research, but also a popular tourist attraction, drawing people from all over the world. Every year, tens of thousands of tourists visit to see this natural wonder and feel the scale of the catastrophe that occurred so recently. This wound on the surface of our planet fills our minds with thoughts about how fragile our Earth is and how quickly changes can occur that alter our accustomed way of life. The meteor crater is a testament to the fact that even the most destructive events can leave their mark on Earth for centuries, allowing us to look into the past and ponder the future. Inside the crater, there are many interesting formations, including ejected rocks and traces of subsequent erosion processes. At the bottom of the crater, there are small lakes that have formed from rainwater collecting in the depression. These water bodies serve as homes for various birds and other animals, creating a unique ecosystem in such a harsh environment. The meteor crater is not just a geological structure. It is a whole history encapsulated in the Earth, a story of how the cosmos interacts with our planet. Each visit here is an opportunity to touch the mysteries that are stored in the depths of this giant wound. The crater is not only a geological but also a cultural object, as it has become a symbol of scientific research in the field of planetary science. The scientific work done here has laid the foundation for many theories about the formation of craters on other planets, such as Mars and the Moon. This crater confirms that Earth is not just a planet, but an active field for studying cosmic processes. The Popigai crater, located in Siberia, is one of the most significant geological formations on the planet. With a diameter of approximately 140 kilometers, it is the second largest impact crater on Earth after the Vredefort crater in South Africa. The impact that formed this crater occurred about 46 million years ago when a giant meteorite, the size of a small city, struck the Earth at tremendous speed. The collision not only created a crater but also unique minerals, among which impact diamonds stand out. These diamonds form under high pressure and temperature conditions associated with impact events and have a unique structure distinct from ordinary diamonds. They can contain inclusions that indicate the conditions of their formation, such as carbon compounds and remnants of other minerals. Impact diamonds from the Popigai crater have become a subject of study for many geologists and mineralogists because their properties can reveal processes that occurred during the impact. This remote location, surrounded by taiga and inaccessible nature, preserves the traces of a cosmic catastrophe that once shook the Earth. The Popigai crater not only amazes with its size but also attracts the attention of scientists who seek to understand how such events affect global climate changes and the development of life on the planet. Studies have shown that after the impact there was a significant change in the atmosphere which could have led to mass extinctions. Scientists have discovered layers of sedimentary rocks in the crater that indicate that powerful tsunamis and forest fires, which covered vast territories, occurred as a result of the impact. Scientific expeditions conducted here have not only recorded diamonds but also other interesting minerals such as shock quartz, which forms during impacts, and numerous fossils left over from this catastrophic event. With each new study, scientists uncover more mysteries hidden in this extraordinary place, which, despite its remoteness, continues to attract the attention of not only geologists but also astronomers studying the influence of cosmic objects on Earth. The Tunguska event occurred on June 23, 1908, and became one of the most mysterious incidents in the history of science. On that day, a powerful explosive event took place over the Siberian taiga, near the Podkamenaya Tunguska River, which, according to estimates, had the force of up to 400 kilotons of TNT. The explosion was so powerful that it was felt over several hundred kilometers from the epicenter, including in Irkutsk, which is more than 600 kilometers away. More than 2,000 square kilometers of forest were destroyed, and trees within a radius of tens of kilometers were felled in a radial pattern, as if struck by a giant hand. This scene of destruction shocked the first researchers who arrived at the site, but another mystery soon emerged. There was no crater, as is usually the case with meteorite impacts. This led to numerous theories, ranging from the hypothesis of a meteorite explosion in the atmosphere to theories about a nuclear explosion. although nuclear technology was not yet known at the time. Investigations were conducted in the harsh conditions of the taiga, which was difficult to reach, especially in the early 20th century when infrastructure was poorly developed. The first expedition, organized in 1932 under the leadership of geologist Leonid Kulik, soon encountered many difficulties, from poor weather conditions to a lack of funds and equipment. Nevertheless, Kulik and his team collected many samples, including glass fragments and unique minerals such as tektites, which could have been formed as a result of a high-temperature explosion. However, even these findings did not provide a definitive explanation for the event. In subsequent years and decades, researchers such as Soviet astronomer Vladimir Sukhov and others continued to return to this remote region, trying to unravel the mystery of the Tunguska event. Each new visit brought hope for new discoveries, but the locality remained inhospitable and many studies ended without clear results. The scientific community has been discussing this phenomenon for more than a century, linking it to possible meteorites, comets, and even experiments related to high technologies. The main question that remains unanswered is what exactly exploded in the sky over Siberia, and why this event, which possessed enormous power, left behind only a destroyed forest and numerous hypotheses but no crater. The Tunguska event remains a symbol of a scientific enigma that can captivate both researchers and lovers of mysteries. Even today, one can find remnants in this place that may one day help reveal the secret hidden behind this mysterious explosion. February 2013 became a fateful year for Chelyabinsk. At 9:20 local time, a deafening explosion was heard over the city, caused by a meteorite bolide that entered the atmosphere at an incredible speed of around 60,000 kilometers per hour. The resulting collision with the atmosphere produced a blinding flash, brighter than sunlight, visible from hundreds of kilometers away. The shock wave from the explosion shattered more than 2,000 windows in homes and buildings, damaged around 700 structures, including schools, hospitals, and administrative buildings. Approximately 6,000 people were injured, most of whom were injured by broken glass and falling debris. The suddenness of this cosmic intrusion into the city's daily life shocked the residents, who in an instant found themselves witnesses to a cosmic threat capable of destroying everything in its path. For several days after the event, scientists and volunteers began searching for fragments of the meteorite, estimated to have a mass of around 7,000 tons and the size of a small car. The main search efforts focused on Lake Chebarkul, where a small crater formed as a result of the impact, with a depth of around 30 centimeters. The first meteorite fragments were found just a few days after the explosion. Local residents and researchers collected several hundred small fragments, which were later studied by scientists from various countries. Among them were pieces weighing from several grams to 1.5 kilograms, with characteristic features such as metallic luster and a unique structure that allowed scientists to determine that these were not ordinary rocks but fragments from space. As a result of the successful search, a collection consisting of more than 700 fragments was assembled, which is now stored in museums and scientific institutions such as the Chelyabinsk State Museum and the Institute of Mineralogy and Geochemistry. This event became not only a scientific sensation but also an important lesson about how vulnerable we can be in the face of cosmic threats. The Chelyabinsk meteor became a symbol of the fact that even in the 21st century, in the era of technology and scientific achievements, humanity is not immune to sudden cosmic catastrophes. Tsunamis are giant waves that occur as a result of powerful underwater earthquakes, landslides, or even meteorite impacts on the ocean surface. These phenomena occur when there is a sudden displacement of the ocean floor, leading to the formation of waves that can travel at speeds of up to 400 kilometers per hour in open ocean. In open water, tsunamis are often imperceptible, with wave heights sometimes measuring only a few dozen centimeters, making the seemingly peaceful ocean hide its latent aggression. However, when a tsunami approaches shallow water, the situation changes dramatically. Water begins to rise and accumulate, and the wave can grow to heights of 30 meters or more, becoming truly devastating in its power. At this time, the shore appears calm, and people are often unaware of the impending danger, making tsunamis particularly treacherous. When the wave crashes onto the shore, it can sweep away everything in its path, destroying buildings, throwing cars onto land, and causing immense damage to infrastructure. As it moves, a tsunami can absorb vast volumes of water, creating powerful currents that carry everything in their path. Studies show that even small earthquakes, registered at depths of more than 100 kilometers, can generate tsunamis if they occur in oceanic plates. For example, an earthquake with a magnitude of 5 or more can produce waves capable of causing significant damage, underscoring the need for careful monitoring of seismic activity. Scientists use special buoys and seismographs for early warning of tsunamis, but unfortunately, this is not always successful, and people sometimes have only a few minutes to save themselves. As a result, tsunamis remain one of the most dangerous natural phenomena, capable of transforming entire regions in a matter of minutes, leaving behind only ruins and destruction. The mechanism of wave formation is an active area of research, as understanding the physical processes involved can help in the development of effective warning systems. It is important to note that tsunamis are not only the result of underwater earthquakes, but also other factors such as landslides, when large masses of earth collapse into the ocean, causing similar waves. For example, the Great Landslide in California, which occurred in 1898, produced waves of significant height. This event served as a lesson for many, demonstrating the importance of preparing for such disasters. Tsunamis, therefore, are not only a geophysical phenomenon, but also an important aspect of oceanography and seismology, highlighting the need for continuous scientific research and development in the field of warning and protection against these destructive forces. The tsunami in the Indian Ocean that occurred on December 26, 2004, was one of the most devastating natural disasters in history, claiming the lives of more than 230,000 people in 14 countries. The cause of this tsunami was a powerful earthquake with a magnitude of 9 on the Richter scale that struck the seabed off the coast of Sumatra in Indonesia at a depth of around 50 kilometers. The energy released during the earthquake was equivalent to that of several atomic bombs and triggered a series of giant waves that moved in different directions at speeds exceeding 300 kilometers per hour, comparable to the speed of a jet aircraft. As the waves approached the coast, their height and power changed depending on the seabed topography and the shape of the shoreline. In open ocean, the waves could reach heights of only a few dozen centimeters, but as they approached land, especially over shallow water, their height increased to 30 meters, crashing onto the coast with deafening roars. In particular, on the coast of Thailand, in the area of the Phuket resort, the waves swept away buildings, carrying people and cars that were on the beach. In Indonesia, at the epicenter of the disaster, on the coast of Sumatra, and on other islands such as Nias and Mentawai, the destruction was immense. Entire villages were washed away, and tens of thousands of people were left homeless. On Sri Lanka, the tsunami flooded coastal areas, and in Colombo, the capital of the country, waves even flooded the tallest buildings. In Myanmar, Malaysia, and the Maldives, significant damage was also observed, but the highest number of casualties was in Indonesia and Sri Lanka. Local authorities and international organizations faced enormous difficulties in providing assistance to the victims, as the infrastructure was completely destroyed and roads were flooded. Rescue operations were further complicated by the lack of communication and the eroded shorelines, making it difficult to evacuate people and deliver humanitarian aid. Scientific research conducted after the disaster highlighted the need for early warning systems to prevent similar tragedies in the future. Scientific organizations such as the U.S. Geological Survey began developing new monitoring and warning technologies that would allow for more effective response to tsunami threats. Thus, the tsunami in the Indian Ocean in 2004 not only claimed many lives but also served as a catalyst for improving warning systems worldwide. The height of the waves in some areas reached 30 meters, one of the highest values recorded for a tsunami in history. The tsunami in the Indian Ocean in 2004 not only caused human casualties but also had a catastrophic impact on coastal ecosystems. According to the World Wildlife Fund, waves destroyed nearly 80% of mangrove forests along the coasts of Indonesia and Sri Lanka. These forests, which serve as natural barriers and habitats for numerous species such as mangrove crabs and fish fry, were threatened by the strong impact of the waves and subsequent flooding. Mangroves not only protect coastlines from erosion, but also play a crucial role in the carbon cycle by absorbing carbon emissions. The destruction of these ecosystems led to a decline in water quality and loss of biodiversity, as many species were unable to adapt to the new conditions. Coral reefs, which were also affected by the tsunami, were destroyed due to the strong turbulence and changes in water temperature. Studies show that in some areas, such as Nicaragua, the level of reef damage reached 70%, affecting fishing communities that depend on these ecosystems. Saltwater intrusion into agricultural lands resulted in significant soil salinization. In some places, the level of salinization reached 30%, making it impossible to grow traditional crops such as rice and sugarcane. The once green and fertile landscapes turned into barren lands, exacerbating the economic difficulties of local residents. The restoration of ecosystems after the tsunami was slow and uneven. In some areas, the restoration of mangrove forests took more than 10 years, with vegetation only beginning to return thanks to the efforts of local ecologists who planted young trees. However, despite these restoration efforts, many animal species did not return as their habitats were destroyed. Coral reefs also began to slowly recover, but the process was complex and required favorable conditions such as stable water temperature and reduced pollution. Ecologists note that the restoration of these ecosystems may take decades and in some cases centuries. In some places, such as the Similan Islands, scientists have observed positive changes, such as an increase in the number of fish and other marine organisms, indicating that nature is gradually recovering. However, despite this optimism, it is important to consider that restoration processes occur under constant threats such as climate change and human activity. Systems that were destroyed require constant monitoring and protection to prevent repeat catastrophes. The restoration of coastal ecosystems is not only an ecological but also a social task, as local communities depend on the resources they provide. It is becoming increasingly clear that for the restoration of life on affected territories, it is necessary to consider not only natural but also social aspects. In some regions, such as the southern part of Indonesia, local residents began to apply methods of sustainable farming to adapt to the changed conditions. These efforts demonstrate that despite all the destruction, life on the coasts of the Indian Ocean continues to find ways to recover. The losses from the tsunami in 2004 served as a lesson not only for ecosystems, but also for people who now realize the importance of preserving the natural balance. Pelago tsunamis are a significant object of study for geologists because they have left clear traces in the geological record, allowing a better understanding of the frequency and scale of such natural disasters in the past. Researchers such as Dr. James G. Murphy, working at the University of Washington, use stratigraphy methods to analyze deposits created by ancient tsunamis. These deposits often contain unique layers of sand and clay formed under the influence of powerful waves capable of moving large volumes of material. For example, in 2008, scientists on the Florida coast found layers up to 1 meter thick formed by a tsunami that occurred around 7,000 years ago. Each layer can tell about the nature and intensity of the wave, as well as the time of its occurrence. Geologists use radiocarbon dating to determine the age of the findings, which allows establishing the chronology of events. Analysis methods include studying marine deposits underwater and investigating coastal lines where traces of wave action are found. In the 2000s, researchers from the University of California, San Diego used boreholes to extract samples that confirmed the presence of paleo-tsunamis in different regions, such as California and Alaska. These data allow not only to restore the history of previous disasters, but also to create models that help predict future risks. For example, in 2009, a team of scientists led by Dr. Richard K. Smith from the Scripps Institution of Oceanography developed computer models based on the found deposits to assess the probability of catastrophic events on the coasts of the Pacific Ocean. Analysis of deposits created by paleo-tsunamis allows not only to evaluate their frequency, but also their scale, which is crucial for preparing for future threats. Research shows that in some regions of the Pacific Ocean, such as the Hawaiian archipelago, paleo-tsunamis occurred with a periodicity of several hundred years, indicating the possibility of destructive events in the near future. In 2001, scientists in Japan discovered traces of paleo-tsunamis that occurred around 500 years ago, and these data played a significant role in developing strategies to reduce risks. Continuous study of paleo-tsunamis helps improve systems for warning and responding to natural disasters, which can save many lives. Comparing data on ancient tsunamis with modern models allows creating more accurate forecasts. For example, in 2006, researchers in Indonesia used paleo-tsunami data to create models predicting how tsunamis could affect various regions after earthquakes. Thus, paleo-tsunamis serve not only as historical evidence, but also as a valuable tool for modern science, allowing the assessment of risks and preparation for future disasters. The discovery and analysis of deposits left by ancient waves remain a key element in understanding the dynamics of the Earth's crust and its impact on ecosystems and human communities. In the 20th century, scientists recorded more than 60 major tsunamis, and each of them left its mark in the geological record. Earthquakes are sudden and unpredictable phenomena that occur as a result of the abrupt displacement of blocks of the Earth's crust. These displacements primarily occur along geological faults, where stress builds up in rocks to a critical point. At this point, bonds between minerals are broken, releasing a massive amount of energy. This process can occur at depths ranging from several kilometers to tens of kilometers below the Earth's surface. When blocks shift, they generate seismic waves that travel through the Earth, causing vibrations in surrounding rocks. There are several types of seismic waves. First, there are P waves, or primary waves, which move through both solid and liquid media, compressing and stretching the material. They are the fastest of all seismic waves and can reach speeds up to 800 kilometers per hour. The second category is S waves, or secondary waves, which move only through solid materials, causing lateral vibrations. S waves are slower than P waves but can have a devastating impact on the surface. Additionally, there are surface waves that travel along the Earth's surface and can cause the most significant damage to buildings and infrastructure. These waves are slower but have a greater amplitude, making them particularly dangerous. When these waves reach the surface, they can cause the ground to shake, creating the sensation that the planet itself is breathing. During this time, destruction can occur instantaneously. Buildings can collapse, bridges can fall, and roads can be torn apart. Studies show that tremors of varying intensity can last from several seconds to several minutes, leaving behind chaos and destruction. The most powerful earthquakes in history have had magnitudes greater than 8 on the Richter scale and caused catastrophic consequences. For example, the earthquake in Chile in 1930, with a magnitude of 8.6, resulted in the loss of more than 50,000 lives and triggered a tsunami that struck the coasts of the entire Pacific Ocean. Earthquakes occur without warning and can happen anywhere on the planet, making them one of the most dangerous natural phenomena. Research by seismologists helps to better understand the mechanisms of their occurrence and predict potential consequences. Different models of seismic activity allow for the assessment of risks and preparation for potential disasters. Scientific work, such as the research conducted by a group of scientists led by Dr. David A. Redfield in 2001, has identified key patterns in the distribution of earthquakes, contributing to more accurate forecasting. However, it is important to note that the impact of earthquakes is not limited to direct destruction. They can also trigger secondary phenomena such as landslides and tsunamis, which exacerbate the consequences of the initial shocks. These natural disasters force us to consider how we can adapt and prepare for such events, changing our approach to construction and urban planning in seismically active regions. It is worth noting that with each new study, we gain more knowledge about how to protect the population and infrastructure from these destructive forces of nature. The Great Lisbon earthquake occurred on November 1, 1755, and had a magnitude of around 8 on the Richter scale, making it one of the most devastating earthquakes in European history. The epicenter was located in the Atlantic Ocean between Lisbon and the Azores. Strong tremors lasted for about 6 minutes, resulting in catastrophic damage in the Portuguese capital. Nearly 90% of the buildings in Lisbon were destroyed, including churches, palaces, and residential homes. Estimates suggest that between 30 and 100,000 people died due to the earthquake, the subsequent tsunami, and the devastating fires. The tsunami, caused by underwater faults, reached heights of up to 30 meters, flooding coastal areas and taking many lives. Fires that broke out after the earthquake engulfed the remaining buildings, leaving Lisbon with almost nothing but ruins. Panic ensued and survivors fled the city, exacerbating the humanitarian crisis. This earthquake not only shook Lisbon, but also the entire Europe, sparking wide-ranging philosophical debates about the nature of evil and divine providence. Philosophers such as Voltaire and Rousseau began to challenge traditional notions of divine justice, questioning how such a terrible event could occur in a world where God exists. Voltaire, in particular, criticized Leibniz's optimistic philosophy, which asserted that all is for the best in the best of all possible worlds. The answer to this question became a significant aspect of philosophical contemplation of the time. These events also laid the foundation for the development of seismology as a science. In the 18th century, the science of earthquakes was just beginning to take shape, and the catastrophe in Lisbon served as a catalyst for more systematic study of these phenomena. Scientists like Charles M. de la Condamine began to investigate the causes of earthquakes and their consequences, leading to the creation of the first seismographs and the development of the theoretical foundations of seismology. Thus, by the end of the 18th century, thanks to these efforts, the basis for understanding tectonic processes and the dynamics of the Earth's crust was established. The Lisbon earthquake not only transformed the city's appearance, but also became a landmark event that left a deep mark on people's minds and in science, raising questions about human existence and interaction with nature. There are also records that the earthquake led to the emergence of numerous sources such as scientific articles and publications which collected information about the catastrophe and its consequences. These records became important for future research in seismology and the humanities. In the night from April 22nd to 23rd, 1906, San Francisco experienced one of the most devastating earthquakes in the history of the United States. The magnitude of the underground tremors reached 8 on the Richter scale, with the epicenter located along the famous San Andreas Fault. This event not only caused destruction but also chaos that engulfed the city. In the first minutes after the earthquake, buildings began to collapse and streets were filled with dust and debris. The areas most affected were those built on sandy and clay soils, which significantly increased the risk of collapse. According to American geologist Dr. James K. Longworth, approximately 80% of the buildings in the city center were destroyed or severely damaged. However, the worst was yet to come after the underground tremors subsided. Serious damage to gas pipelines and stoves led to numerous fires. The flames spread to entire quarters, sometimes destroying residential buildings faster than the earthquakes themselves. It is estimated that the fire destroyed more than 30% of the city, leaving hundreds of thousands of people homeless. Firefighters who tried to control the fire faced enormous difficulties, as water in the reservoirs was insufficient and the destroyed roads hindered access to water sources. As a result, many buildings that could have been saved were burned to the ground. For 3 days after the earthquake, the fire continued to rage, and it was only when the wind changed direction and rain finally came to the city that the main fires were extinguished. The losses from the fires are estimated at around $4 billion in today's terms, making this incident one of the most expensive natural disasters in the history of the United States. As a result of the earthquake and subsequent fires, approximately 13,000 people lost their lives. The city, once vibrant and prosperous, was reduced to ruins that left deep scars in the hearts of its residents. All that remained of the once magnificent buildings were charred shells, and the memory of the catastrophe remained etched in history. The reconstruction of the city took many years, and it was not until the 1910s that San Francisco began to return to life. Devastating earthquakes, similar to those that shook San Francisco, became catalysts for the development of earthquake-resistant construction. Following the 1906 catastrophe, engineers and architects began actively studying how to create buildings capable of withstanding ground tremors. One of the first steps in this direction was the implementation of damping technologies. This method reduces the vibrations of the structure during an earthquake using special devices such as dampers and shock absorbers. In the 1980s, Japanese engineers developed a system known as smart foundations that can change their stiffness based on the strength of the tremors. For example, buildings in Tokyo were constructed with such foundations that can adapt to changing conditions and absorb the energy of seismic waves. Flexible structures also became a crucial element of earthquake-resistant construction. Instead of rigid and immovable walls, modern buildings are designed to dance during an earthquake. For instance, in the 1990s, the Transamerica Pyramid in California was built with a unique shape and structure that allows it to bend under the force of earthquakes. The use of modern materials, such as reinforced concrete and fiberglass, also plays a key role in earthquake-resistant construction. These materials possess high strength and lightness, enabling the creation of safer and more stable structures. In the 2000s, architects began using computer modeling, which allowed them to predict the behavior of buildings under various seismic conditions. They can simulate how a building will react to different levels of seismic activity, enabling changes to be made to the design at early stages. Standards for earthquake-resistant design have been evolving and tightening since the 1960s, when seismic codes for construction were first introduced in California. These codes require builders to consider the location of the building, its height and mass, as well as the seismic activity of the region. As a result of the application of all these technologies and methods, mortality and destruction from earthquakes have been significantly reduced. For example, during the 1994 earthquake in Northridge, California, buildings constructed according to new standards suffered significantly less damage compared to those built before the implementation of earthquake-resistant technologies. Ultimately, the development of earthquake-resistant construction not only saves lives but also ensures sustainable development of cities in earthquake-prone regions such as Japan and the United States. Early warning systems for earthquakes consist of complex networks of seismometers placed in strategically important locations, capable of detecting even the slightest tremors. For instance, Japan operates one of the most advanced systems, known as JMA, Japan Meteorological Agency, which includes over 400 seismometers across the country. These devices instantly record seismic waves generated by earthquakes and transmit data to a central computer cluster. The data processing algorithms used in such systems can analyze incoming signals in just a few seconds to determine the epicenter, depth, and magnitude of an earthquake. A study conducted in 2008 showed that these algorithms can provide warnings 8 seconds before destructive waves reach populated areas. These 8 seconds may seem insignificant, but they can save lives by allowing people to take shelter in safe places. In Los Angeles, for example, the Shake Alert system, designed to protect the population, uses over 60 seismometers. It is designed to warn residents 30 seconds before a strong shock. Signals from seismometers are processed using machine learning algorithms that improve prediction accuracy with each new seismic event. Alerts are sent to mobile devices, public institutions, and even companies in the high-tech sector, such as Tesla and Google, which can automatically stop production lines and evacuate employees. In 2000, California implemented a neighborhood alert concept, which allows residents to receive notifications via local radio stations, SMS messages, and even loudspeaker systems. This initiative significantly increased public awareness and preparedness for potential disasters. Early warning systems not only ensure safety but also help minimize economic losses. For example, in 2017, after the Shake Alert system successfully predicted an earthquake of magnitude 6.2, it was possible to avoid $1 billion in damage due to timely warnings. Each time seismometers detect tremors, a race against time begins, where every second counts. In 2011, after the earthquake in Tohoku, the JMA system demonstrated its effectiveness by providing residents of Tokyo around 30 seconds to take shelter. Alerts were received via mobile phones, televisions, and radio broadcasts, which helped minimize the number of casualties. The effectiveness of such systems depends not only on technology, but also on the level of public preparedness. Japan has conducted extensive educational programs that teach people how to act in case of an earthquake, significantly increasing the chances of survival. With each new earthquake, systems become more sophisticated and algorithms become more accurate. In 2020, specialists from the University of Tokyo developed a new data processing model that significantly speeds up the reaction time. This progress in earthquake prediction became possible thanks to a multidisciplinary approach that combined seismologists, engineers, and information technology specialists. The climate of Earth is not a static quantity but a dynamic system that has undergone numerous changes over millions of years. Scientific research shows that our planet has experienced diverse climatic conditions, ranging from greenhouse periods, when temperatures were significantly higher than today, to Ice Age epochs, when vast ice sheets covered substantial parts of the land. For instance, during greenhouse periods, the level of carbon dioxide in the atmosphere could reach over 1,000 parts per million, leading to an increase in average temperature by tens of degrees. During these times, forests grew even in areas that are now deserts, and sea levels rose by tens of meters, flooding coastal zones. These warm periods were followed by ice ages when temperatures dropped sharply and glaciers extended to latitudes where major cities like New York and London are now located. It is interesting that with each new ice age, significant changes in ecosystems occurred, with many species going extinct and others adapting, demonstrating the flexibility of the biosphere. Geological data, such as the analysis of ice cores and sedimentary rocks, help scientists reconstruct the climatic conditions of past epochs. For example, research on ice cores from Greenland and Antarctica shows that over the last 800,000 years, Earth has experienced at least 8 ice ages and interglacial periods. These climate changes were caused by various factors, including changes in solar activity, fluctuations in Earth's orbit, and tectonic processes. Specifically, as continents moved, ocean currents changed, which also influenced the climate. Thus, each new epoch, whether warm or cold, left its mark on the planet, shaping landscapes, ecosystems, and even human cultural practices. Climate change models indicate that these cycles will continue and the climate of Earth will change repeatedly, as it has done over billions of years. Currently, the average temperature on the planet is 1 degree higher than in the pre-industrial era, and this change is already causing noticeable consequences, such as the melting of glaciers and the rise in sea level. According to projections in the 20th century, temperature may rise by an additional 2 to 3 degrees, leading to serious consequences for ecosystems and humanity. Comparing contemporary climate changes with historical data underscores the uniqueness of the current situation. The rate at which climate change is occurring is tens of times faster than the pace of past changes, threatening the stability of many ecosystems. Scientific research shows that if no measures are taken, sea levels could rise by 1 meter by the end of the 20th century, flooding millions of hectares of coastal territories. The Paleocene-Eocene thermal maximum occurred approximately 56 million years ago and was one of the most significant climatic catastrophes in Earth's history. During this period, the surface temperature of the oceans rose by 5 to 7 degrees Celsius, leading to rapid changes in global climate. This warming occurred just a few million years after the mass extinction event known as the Cretaceous-Paleogene extinction, which saw the disappearance of dinosaurs and many other species. The global temperature increase facilitated the expansion of tropical ecosystems northward, altering the familiar climate in regions such as North America and Europe. As the warming progressed, marine ecosystems underwent significant changes. The abundance of carbon in the atmosphere increased, leading to the expansion of anaerobic zones in the oceans and the formation of dead zones, where life was almost absent. This also resulted in shifts in the ranges of plants and animals. Tropical forests began to spread to higher latitudes, and in some places such as modern-day Canada and Alaska, tropical plant species like palms appeared. Some groups of organisms adapted to the new conditions, such as mammals, which diversified and evolved, while others, such as marine mollusks and corals, struggled to survive and reduced their ranges. There was also a significant impact on the faunal composition. Many species, such as ancient whales and primates, began to appear and evolved during this time, driven by changes in ecosystems. Adaptations to the new climatic conditions were evident in changes in the size and shape of organisms, allowing them to better survive in the conditions of increased temperature and changing oxygen levels in the water. The increase in temperature also accelerated the decomposition of organic matter, affecting the oxygen levels in the oceans, and many marine organisms were unable to adapt to these changes. This was a period when ecosystems were restructuring, and many species that could not adapt went extinct. Research shows that the Paleocene-Eocene thermal maximum was a crucial stage in Earth's evolution, as it prepared the ground for the emergence of new species and ecosystems. This period lasted approximately 2 million years and ended with a drop in temperatures, returning the planet to more moderate climatic conditions. As a result of this global warming in the oceans, significant changes occurred, such as the increased activation of methane from sedimentary deposits, which could have further accelerated climate warming. The level of carbon dioxide in the atmosphere during this time reached values comparable to the present, drawing parallels with current climate changes. The Paleocene-Eocene thermal maximum occurred around 56 million years ago, when the planet's temperature rose by approximately 5 to 6 degrees Celsius. The primary cause of this global warming was massive methane releases from methane hydrates located on the ocean floors. These methane hydrates are crystalline structures that contain methane frozen in water under high pressure and low temperature. Even a slight increase in temperature can cause these crystals to decompose, releasing methane into the atmosphere. Methane, with its 25 times greater greenhouse effect than carbon dioxide, began to accumulate in the atmosphere, significantly enhancing the greenhouse effect. This process became a self-reinforcing cycle. Initial warming led to methane release, which in turn contributed to further temperature rise. Research indicates that during this period, methane levels in the atmosphere reached values 2 to 3 times higher than current levels. As a result, the increased ocean temperatures further decomposed methane hydrates, creating a feedback loop that destabilized the planet's climate system. Scientific data from ice cores in Greenland and Antarctica show sharp fluctuations in carbon dioxide and methane levels, indicating active interaction between climate and carbon reservoirs. Around the same time, changes in ocean circulation were observed, confirmed by the analysis of sedimentary rocks, indicating warmer and less oxygenated waters, which negatively impacted marine ecosystems. Mass extinctions of marine species also occurred during this time, possibly linked to changes in ocean chemistry. Thus, the Paleocene-Eocene thermal maximum serves as a striking example of how small climate changes can lead to catastrophic consequences, creating positive feedback loops and destabilizing ecosystems. This phenomenon clearly illustrates how the planet responds to temperature changes, highlighting the fragility of the climate system. The volume of methane released during this period is estimated to be in the billions of tons, significantly impacting global climate models. Scientific research has revealed that a phenomenon known as snowball Earth could have existed in several periods throughout the history of our planet. One of the most well-known periods occurred approximately between 80 and 70 million years ago, when the planet experienced extreme climatic conditions. During this time, glaciers covered almost the entire land surface, including equatorial regions, creating a harsh environment for life. Oceans froze up to the equator, significantly lowering water temperatures and virtually halting photosynthesis. This meant that the primary food sources for most organisms disappeared, putting many species at risk of extinction. In such conditions, life could only survive in limited refuges, such as hot springs and deep-sea hydrothermal vents, which provided the necessary heat and chemical compounds to sustain ecosystems. For example, in oceanic ecosystems, hydrothermal sources produce hydrogen sulfide, which serves as an energy source for microbes, thereby supporting food chains. Subglacial bodies of water could also have become important refuges, where temperatures remained above zero, allowing some species to survive. One of the key characteristics of such epochs is that they created conditions that led to the evolution of organisms adapted to extreme conditions. It is known that such ice ages could have lasted for millions of years, with one of them, called Cryogen Earth, occurring around 600 million years ago. During this time, ice covered even equatorial zones, making the planet almost unrecognizable. Paleontological findings show that in the conditions of snowball Earth, only specialized species that could adapt to low temperatures and lack of light survived. For instance, in such conditions, the ancestors of modern single-celled organisms and some multicellular organisms survived, which could use chemosynthesis to obtain energy. Research indicates that such extreme climatic changes could have led to mass extinctions, when many species were unable to adapt to the new conditions. The era of snowball Earth illustrates how climatic changes can have a profound impact on the biosphere and the evolution of life on the planet. It is important to note that even in the harshest conditions, life found ways to survive and adapt, highlighting its resilience. In subsequent epochs, when the climate became more favorable, life on Earth flourished again, but the consequences of snowball Earth are still felt in modern ecosystems, and studying these periods helps us understand how climatic changes can affect life on our planet. One of the most well-known findings related to this period was made in Siberia, where the remains of ancient organisms adapted to cold conditions were discovered, confirming the existence of complex ecosystems even in the most unfavorable conditions. The world gradually emerged from the snowball Earth state due to the accumulation of volcanic gases in the atmosphere. Over millions of years, starting roughly from the end of the Triassic period, about 200 million years ago, volcanic activity on the planet increased. Volcanoes, such as the supervolcano Yellowstone in North America, released enormous volumes of carbon dioxide and sulfur dioxide, significantly increasing the concentration of greenhouse gases in the atmosphere. This process was further intensified by eruptions like the catastrophic eruption of the Toba volcano on Sumatra around 70,000 years ago, which caused global cooling for several centuries. However, while some regions emerged from the Ice Age, others, such as Siberia, continued to have extensive ice covers. As the concentration of carbon dioxide increased, the greenhouse effect began to gain strength, acting as a catalyst for rapid warming. According to researchers from Princeton University, each percentage increase in carbon dioxide led to a temperature rise of several tenths of a degree. Approximately 100,000 years after the start of this process, the Earth's temperature rose by 10 degrees Celsius, which was sufficient to initiate the melting of glaciers. This was akin to an explosion. The temperature rose sharply and the ice masses began to melt rapidly, forming large bodies of water and raising sea levels. The rapid melting of glaciers not only altered the landscape, but also affected ecosystems. The ice that previously covered large areas of land became a source of fresh water, leading to the formation of new ecosystems. The increase in temperature also accelerated erosion processes, opening new lands for vegetation. Around 100,000 years ago in Europe, forests began to appear, changing the ecosystem of the region. Scientists note that such changes facilitated the evolution of new animal and plant species that could adapt to the changing climatic conditions. The mechanism of exiting the snowball Earth state became a true drama, as the Earth, covered in cold and ice, entered a new phase of life. With each decade, the temperature continued to rise, and so did the number of ecosystems that adapted to the new conditions. This was a moment when the planet began to recover and develop, breaking free from the icy grip. Scientists from the Institute of Geochemistry and Ecology in Moscow emphasized that it was during this period that active migration of animals to the north began, leading to the formation of new ecosystems. As a result, by the end of the last ice age, around 10,000 years ago, sea levels rose by more than 100 meters, changing coastal lines and contributing to the formation of modern continents. Scientific research shows that this transition from an icy world to a warm climate was not just a random event. It was the result of a complex interaction of volcanic activity, atmospheric changes, and ecosystem adaptations that shaped our planet as we know it today. Scientific data indicate that over the past 2 million years, Earth has experienced several cycles of glaciation and warming, and this cycle was one of the most dramatic changes in the planet's history. By the end of the last glacial maximum, around 20,000 years ago, the Earth's climate system had already significantly transformed, creating conditions for the emergence of the first civilization. Massive extinction of animals and plants in the Anthropocene is a phenomenon that attracts the attention of scientists and ecologists worldwide. According to data published in the journal Nature in 2019, the rate of species extinction in our time is tens to hundreds of times higher than the natural background extinction rate that was characteristic of previous geological epochs. The causes of this phenomenon are mainly related to human activity, destruction of natural habitats, environmental pollution, climate change, and excessive exploitation of natural resources. For example, according to the World Wildlife Fund, since 1970, the populations of wild animals have decreased by an average of 80%. This process has serious consequences for ecosystems, as the disappearance of one species can trigger a chain reaction affecting other species and the entire ecosystem. The uniqueness of the current mass extinction lies in the fact that it is not due to natural causes, but to the activity of one dominant species, the human. Unlike previous mass extinctions such as the extinction of the dinosaurs, when climate changes and asteroid impacts played a key role, today human activity has become the main driver of these changes. There are studies, such as the work of biologist Edward Wilson, who asserts that if no urgent measures are taken, by the end of the 21st century, we may lose up to half of all species on the planet. The problem is exacerbated by the fact that many disappearing species have not even been fully described by science, making their loss even more tragic. Preserving biodiversity has become one of the most important tasks of our time, as each disappearing form of life is not just a loss, but also a loss of unique genetic resources and ecosystem services that they provide. For instance, tropical forests, which are home to 1 million species, continue to be cut down at rates of up to 12 million hectares per year, leading to unprecedented levels of biodiversity loss. According to the UN, more than 1 billion people depend directly on ecosystem services that healthy ecosystems provide, and their destruction threatens not only biodiversity, but also the very existence of humanity. The destruction of habitats, hunting, fishing, and climate change, all these factors are interconnected and exacerbate the situation, creating a vicious circle of threats. It is important to understand that the loss of even one species can lead to the destruction of entire ecosystems, which ultimately affects the health and well-being of humanity. Data show that in the last decades, the impact of humans on nature has become so strong that some scientists call this phenomenon the sixth mass extinction. According to estimates, more than 30% of all amphibians, 33% of all marine mammals, and almost 40% of all fish species are at risk of extinction. Thus, anthropogenic factors such as climate change, urbanization, and pollution play a key role in this process, and their impact on biodiversity is felt in every corner of the planet. Approximately 30,000 years ago in Australia, giant marsupials such as the Megatherium, enormous lizards up to 7 meters long, and Diprotodon, the largest marsupial mammal weighing up to 2 tons, began to disappear. This disappearance was a consequence of the arrival of the first humans on the continent. The Australian fauna, which had evolved in isolation for millions of years, was unfamiliar with such predators as humans and therefore could not develop effective defense mechanisms. This made it particularly vulnerable. The first Aborigines hunting large herbivores not only decimated animal populations but also had a significant impact on ecosystems. The disappearance of such large species as Diprotodon led to changes in vegetation because these animals played a crucial role in maintaining ecosystem balance. Their herbivorous habits contributed to the spread of certain plant species, and their disappearance altered the structure of flora. For example, without large herbivores controlling the growth of shrubs and trees, many plant species began to spread, which in turn changed the fire regimes. An increase in biomass created conditions for more intense and frequent forest fires, which became a part of the Australian ecosystem. These changes in ecosystems caused by the disappearance of megafauna also affected other animal and plant species. Some species that depended on open spaces began to die out due to changes in their habitat, leading to further reduction in biological diversity. By the time Europeans arrived in Australia in the 18th century, many of these large mammals had already disappeared, and the continent became home to smaller species that could adapt to the new conditions. Scientific research shows that megafauna disappeared not only due to hunting, but also due to climate change that began around 20,000 years ago, when the last ice age ended. However, it was the interaction with humans that became the catalyst for this process. With each new generation of Aborigines, hunting became more effective, leading to a rapid decline in the number of megafauna. The disappearance of giant marsupials and large reptiles was one of the first examples of mass extinction caused by humans, highlighting the significance of our impact on nature. Scientists like Professor John Wilson from the University of Melbourne emphasize that studying these processes can help us understand how modern humanity can influence the environment and what lessons can be learned from the past. For example, the disappearance of Diprotodon led to the dominance of smaller plant species that were previously suppressed by large herbivores, altering the structure of local ecosystems. Thus, The disappearance of megafauna not only deprived Australia of unique animals, but also fundamentally changed its ecosystems, creating conditions for new but less resilient forms of life. Dodo, or dodo, was a flightless pigeon that inhabited the island of Mauritius, which was discovered by Europeans at the end of the 16th century. The dodo was impressive in appearance. Its body could reach a height of 1 meter and weigh around 10 kilograms. This unique species became a symbol of the tragedy that befell ecosystems when humans invaded an undeservedly peaceful corner of nature. The first Europeans who landed on Mauritius in 1682 did not understand that dodos, lacking natural predators on their island, had lost the instincts necessary for survival. These birds not only could not fly, but also built their nests on the ground, making them particularly vulnerable. Within a short period of less than 100 years, the dodo was completely wiped out. The main factors in its extinction were hunting, introduced predators, and habitat destruction. During the 17th century, sailors arriving on Mauritius hunted dodos for easy food. Additionally, pigs, cats, and rats introduced to the island destroyed dodo eggs and chicks, leading to a sharp decline in the population. By the 1670s, it was estimated that there were only a few dozen individuals left, and by 1683, the dodo had disappeared from the face of the earth. The sad story of the dodo served as a stark example of how human intervention can destroy fragile ecosystems. The disappearance of the dodo on the island of Mauritius led to a fundamental change in the balance of local flora and fauna, and many plants that depended on dodos for seed dispersal also began to disappear. The 18th century witnessed the complete disappearance not only of the dodo, but also of many other unique species for which Mauritius was their only home. Interestingly, the dodo became a symbol of an ecological catastrophe and a lesson for future generations, demonstrating how quickly nature can lose its unique species. Currently, only fragments of descriptions of the dodo left by early naturalists such as Georges Cuvier, who in 1863 attempted to reconstruct the image of the dodo from preserved bones, remain. Thus, the dodo became one of the first victims of human activity, and its disappearance served as a harbinger of many ecological catastrophes that followed. Modern methods of preserving endangered species involve complex and multi-layered approaches aimed at preventing new extinctions and preserving biodiversity. One of the most well-known methods is captive breeding programs, which are actively used for species like the Amur tiger, which is on the brink of extinction. In Russia, for example, with the support of the World Wildlife Fund, WWF, special centers have been established where tigers are bred for subsequent release into their natural habitats. According to WWF, as of the beginning of 2020, there were around 400 Amur tigers worldwide, and efforts to breed them have increased this number by 30% over the past 10 years. Genetic material cryopreservation is also becoming a key tool in the fight to save species. This method allows cells, seeds, and other biological materials to be frozen and stored, providing a chance for population restoration in the future. A notable example is the Seed Cryopreservation Project in Norway at Svalbard, where over 1 million seed samples from around the world are stored. This global seed bank was established in 2008 and serves as an insurance policy against ecological disasters or climate change. Restoring ecosystems is also a crucial area of work for environmental organizations. Scientists are actively engaged in restoring ecosystems such as mangrove forests and coral reefs, which play a vital role in maintaining biodiversity. An example of this approach is the project to restore coral reefs on the Great Barrier Reef in Australia, which includes methods such as transplanting healthy corals and creating artificial reefs. Since the early 2000s, over 1 million corals have been transplanted, helping to restore around 10% of severely damaged reef areas. Scientists also use monitoring technologies, such as drones and satellite imagery, to track the condition of ecosystems and populations of rare species. This allows for quick responses and protective measures. Environmental organizations, such as the International Union for Conservation of Nature, IUCN, are actively working on creating red lists of species at risk of extinction, which helps manage programs for their protection. As of 2020, the IUCN list included more than 32,000 animal and plant species at risk of extinction. These efforts by scientists and environmental organizations are aimed at preventing new extinctions and preserving biodiversity for future generations. As of 2023, data shows that more than 40% of all amphibians are at risk of extinction, underscoring the need for swift action. Anthropogenic climate change is a phenomenon caused by human activity that leads to changes in global climate conditions. The primary mechanism driving this process is the increase in the concentration of greenhouse gases in the atmosphere, such as carbon dioxide, methane, and nitrous oxide. Since the start of the Industrial Revolution in the 18th century, the level of carbon dioxide in the atmosphere has risen by more than 40%, primarily due to the burning of fossil fuels, deforestation, and other human activities. Carbon dioxide, when present in the atmosphere, traps heat, creating a greenhouse effect that hinders its escape into space. This process results in an increase in the average global temperature, which in turn accelerates the melting of glaciers, the rise of sea levels, and changes in weather patterns. For example, an increase in temperature leads to more frequent and intense weather events, such as hurricanes and droughts. Simultaneously, human activities alter natural ecosystems, disrupting natural climate processes. Deforestation of tropical forests, which play a crucial role in the carbon cycle, increases the concentration of carbon dioxide in the atmosphere as trees that absorb this gas disappear. As a result, there is an imbalance in the planet's climate system, and ecosystems that were once stable begin to experience stress and change. This creates a vicious circle. Climate change causes changes in ecosystems, which in turn exacerbate anthropogenic impacts. The 18th and 19th centuries witnessed a significant increase in population and industrialization, which also contributed to a substantial increase in greenhouse gas emissions. Contemporary research shows that even small changes in the concentration of greenhouse gases can lead to significant changes in the climate system. For instance, according to the Intergovernmental Panel on Climate Change, even an increase in temperature of 1 degree Celsius can result in serious changes in weather patterns. With each decade, the amount of emissions increases, intensifying the greenhouse effect and leading to further planetary warming. It is predicted that by the end of the 21st century, temperatures could rise by 3 to 4 degrees Celsius if no measures are taken to reduce emissions. Research indicates that such changes are already affecting biological cycles, such as the seasonal migrations of birds and the blooming of plants. When ecosystems cannot adapt to new conditions, this can lead to the extinction of species and the loss of biodiversity. As a result of anthropogenic factors, ocean currents are also changing, and ocean acidity is increasing, affecting marine ecosystems. The growing threat of climate change requires immediate global action, as the consequences can be unpredictable and irreversible. As of 2023, the level of acidity in the oceans has increased by more than 30% since the beginning of the industrial era. The melting of Arctic ice is happening at an alarming rate, and this phenomenon has serious consequences for ecosystems and indigenous peoples living in these regions. According to the National Oceanic and Atmospheric Administration of the United States, the area of sea ice in the Arctic has decreased by almost 70% since the beginning of the 20th century. In 2020, the minimum extent of sea ice was just 3 million square kilometers, the lowest on record. The reduction in sea ice leads to the replacement of the white surface, which reflects solar radiation, with dark water, which absorbs significantly more heat. This creates a positive feedback loop. The less ice there is, the faster the ocean heats up, which in turn leads to even more ice melt. Scientists estimate that by the end of the century, the Arctic could be almost ice-free in the summer months if current trends continue. This change affects local ecosystems. The disappearance of ice makes it difficult for animals like bears and seals to access their usual habitats. For indigenous peoples, such as the Inuit, the reduction in ice means the loss of traditional hunting and fishing routes. As a result of climate change, their lives become increasingly challenging as they face new challenges in finding food and resources. Additionally, the melting of Arctic ice releases methane, a potent greenhouse gas stored in frozen soil layers, exacerbating global warming. Studies show that this process could increase atmospheric methane levels by 30%, creating additional challenges in combating climate change. Climate change models developed in the 2000s show that the Arctic is warming at 2 to 3 times the rate of other regions on the planet, as evidenced by a 2 degrees Celsius increase in air temperature over the past 30 years. Meanwhile, the melting of ice opens up new maritime routes, such as the Northern Sea Route, creating opportunities for commercial navigation, but also intensifying competition for resources, which could lead to conflicts. Studies indicate that by 2025, Arctic maritime traffic could increase by more than 300% compared to 2010. These changes are not just a result of global warming, they have a significant impact on the entire planet, creating new climatic conditions that could affect agriculture, water supply, and ecosystems on other continents. The melting of Arctic ice is not just a local problem, it is a global challenge that requires the collective efforts of all countries to address it. The Arctic, as one of the most vulnerable ecosystems, underscores how seriously humanity must take climate change. In 2023, scientists estimated the thickness of ice in some Arctic regions to be less than 1 meter, a critical level for maintaining the ecosystem. Glaciers in Greenland and Antarctica are losing stability at an alarming rate, as confirmed by research conducted by NASA and other scientific institutions. For instance, since 2010, the annual ice loss in Greenland has increased to 32 billion tons, while in Antarctica, this figure stands at around 36 billion tons per year. In the 21st century, there has been a significant acceleration in the movement of outlet glaciers, such as the Thwaites Glacier in Antarctica, which, according to data, has been moving at a record speed of almost 18 meters per year. This movement is due to the penetration of warm ocean waters under the ice shields, causing them to melt and reducing their stability. As a result, giant icebergs are formed, which break off from the main glacier. In 2006, an iceberg the size of an island with an area of 992 square kilometers broke off from the Larsen B Glacier in Antarctica, becoming one of the largest events in the history of glacier change observations. Such events are becoming increasingly frequent. For example, in 2018, the Pine Island Glacier lost a piece of ice the size of Manhattan. These icebergs, breaking away from the continental glaciers, begin to drift in the ocean, which can significantly affect sea levels. In 2020, it was recorded that sea levels had risen by 7 millimeters over the past 10 years, which is directly related to ice loss in polar regions. The problem is exacerbated by the fact that the melting of glaciers leads to a feedback loop. The less ice there is, the faster the ocean absorbs solar heat, which in turn accelerates the melting process. As a result, by the 2030s, according to experts' forecasts, sea levels could rise by 1 meter if the melting rates do not slow down. This could have catastrophic consequences for coastal cities and ecosystems worldwide. In 2020, Dr. Christopher Salonen from the University of Washington State confirmed that even if we reduce carbon emissions, glaciers will continue to lose mass for decades. With each passing year, the process becomes more apparent and clearly demonstrates how the slow but inexorable transformation of polar regions can change the climate picture of the entire planet. Sea level rise is occurring due to two main processes: melting of glaciers and thermal expansion of ocean waters. In 2020, a study conducted by a group of scientists led by Dr. Lars Fenster from the Institute of Oceanography in Seattle showed that the sea level is rising at an average rate of 3 millimeters per year, which is the highest rate in several decades. Greenland and Antarctica are losing massive amounts of ice, with the National Oceanic and Atmospheric Administration of the United States estimating that Greenland alone lost more than 36 billion tons of ice annually from 2001 to 2018. Thermal expansion caused by the warming of ocean waters adds another 2 millimeters to this rate. The vulnerability of coastal cities and island nations is becoming increasingly apparent. For instance, in low-lying areas like Bangladesh, more than 60 million people live less than 1 meter above sea level, and even a slight rise in sea level could lead to the flooding of significant land areas. In 2009, due to sea level rise-induced floods, more than 3 million people were forced to leave their homes. Island nations like the Maldives also face the threat of disappearance. According to the World Bank, by 2030, a significant portion of the Maldives' territory may be submerged, putting the very existence of the nation at risk. The need for infrastructure adaptation is becoming critically important. For example, in Singapore, authorities plan to invest more than $21 billion in projects to strengthen coastlines and build new drainage systems to cope with the effects of climate change. In 2018, the Netherlands adopted a comprehensive plan to protect against floods. The program includes the construction of new barriers and the expansion of existing ones, which will help protect populated areas below sea level. It is expected that the migration of populations from flooded areas will become one of the most serious humanitarian issues in the future. According to the UN, by 2050, around 200 million people may become internal migrants due to sea level rise. In countries like Vietnam, where the Mekong Delta is prone to flooding, the population is already seeking safe places to live, creating additional challenges for receiving countries that may face social and economic consequences of a large influx of migrants. In Australia, for example, authorities are developing plans to relocate residents from low-lying areas. In 2009, due to floods in Queensland, more than 25,000 people were evacuated, demonstrating how climate change is already affecting people's lives. In other regions, such as the Caribbean, governments are considering the creation of new, safer settlements for residents of islands prone to flooding. Meanwhile, in countries like the Philippines, local communities are actively working on projects to restore ecosystems, such as the regeneration of mangrove forests, which can serve as natural protection against floods and hurricanes. As a result, sea level rise is becoming not just an ecological issue, but also a complex social and economic problem requiring urgent attention. In 2020, a study conducted by the World Bank showed that countries most vulnerable to climate change could lose up to 30% of their gross domestic product by 2030 if adaptation measures are not taken. In such circumstances, it is necessary to develop global strategies aimed at protecting the most vulnerable regions and maintaining the resilience of local communities. Changes in precipitation patterns due to global warming are becoming one of the most pressing problems affecting agriculture and urban infrastructure. Over the past decades, there has been a significant increase in the frequency and intensity of extreme weather events. For instance, according to the Intergovernmental Panel on Climate Change report, the frequency and intensity of droughts have increased by 30% in regions such as South Africa and parts of Australia since 2010. Simultaneously, in other areas like South Asia and the eastern coast of the United States, there has been an increase in the number of floods, indicating an uneven distribution of precipitation. In 2020, India experienced over 136 millimeters of rain in just 12 hours in some regions, leading to catastrophic consequences and loss of life. The increase in precipitation intensity in certain regions poses a threat to existing urban infrastructure, which often cannot withstand such loads. In cities like Mumbai, drainage systems cannot handle sudden downpours, resulting in flooding and road destruction, which hinders the movement of residents and food supplies. Meanwhile, in arid regions such as California, droughts are becoming more prolonged and intense, leading to the depletion of groundwater reserves. In 2019, over 7 million people in this state faced water shortages, threatening not only agriculture, but also daily life. Traditional farming methods based on predictable precipitation patterns are no longer effective. Farmers are forced to adapt to new conditions by using drought-resistant crops and modern technologies such as drip irrigation. However, these methods require significant financial investment and access to new technologies, which is not always possible for small farmers. The unpredictability of weather conditions also impacts urban infrastructure planning. The construction of new residential complexes and roads requires a thorough risk assessment related to potential floods and droughts. In some cases, this leads to construction delays and increased costs. For example, in New York, over $100 million was spent on strengthening the coastline in response to Hurricane Sandy in 2012. This hurricane demonstrated how climate change can affect sea levels and cause destruction in coastal areas. Studies show that by 2030, sea levels may rise by 1 meter, leading to the flooding of significant territories. Adapting to these changes requires a comprehensive approach and interdisciplinary cooperation between governments, scientists, and local communities. It is expected that in the face of increasing climate unpredictability, traditional farming and urban planning methods will face constant challenges. In some countries, such as the Netherlands, systems for protecting against floods have been developed, but this requires time and resources. The development of new technologies and methods for managing water resources is not just a necessity, but a matter of survival. Geoengineering is a deliberate human intervention in Earth's climate system aimed at counteracting global warming. This concept encompasses a wide range of methods, from carbon capture to altering the planet's albedo, with the primary goal of slowing down or even reversing the effects of climate change. Scientific debates around geoengineering raise numerous ethical questions related to the risks that could arise from such interventions. For instance, the carbon capture concept implemented in several countries raises concerns about potential long-term impacts on ecosystems, as it is unclear how such technologies will affect soil and water resources. Studies show that in some cases, such as increasing the concentration of carbon dioxide in the atmosphere, it is necessary to consider not only the effectiveness of the methods, but also the potential health risks for humans. Interfering with the climate system can lead to highly unpredictable consequences, such as changes in weather patterns, which in turn could cause catastrophic effects for agriculture and ecosystems. Global warming is already leading to extreme weather conditions, such as hurricanes and wildfires, and the question arises as to whether it is worth taking risks with new technologies when the consequences of climate change are already evident. Scientists like Dr. Catherine Hayhoe emphasize that inaction could have more serious consequences than the risks associated with geoengineering, but the decision-making process remains complex. Leading researchers like Professor James Hansen argue that intervention may be the only way to avoid catastrophe, but this intervention must be well planned and considered. At the same time, society must be prepared for discussions and assessments of potential consequences, as insufficient awareness can lead to panic and mistrust. The complexity of choosing between the risks of inaction and the potential unpredictable consequences of active intervention underscores the need for open debates and scientific research to find the optimal path. These issues become particularly relevant in light of current global events, such as the floods in Australia, which affect millions of people and raise questions about how much control humanity has over its fate. Some experts, like Professor Kimberly Cartwright, suggest that in the face of a climate crisis, every country should participate in discussions about geoengineering solutions to avoid a global catastrophe. Critics, including Dr. Bill McKibben, warned that excessive reliance on technologies could distract from the need to reduce carbon emissions. It is important to remember that any intervention in the climate system can have its own consequences, and a thorough analysis of each method is required. Studies show that some countries are already developing their own geoengineering strategies, leading to international debates about how to regulate these technologies. For example, in 2020, at an international conference, questions of ethics and safety related to possible actions were discussed. It is important to consider that each decision in this area can have far-reaching consequences not only for the environment, but also for social structures. Stratospheric aerosol spraying technology, known as solar geoengineering, involves a method aimed at reflecting solar radiation and temporarily reducing global temperature. This technique mimics the effect of volcanic eruptions, where particles are injected into the atmosphere to block sunlight. For instance, the eruption of Mount Pinatubo in 1991 led to a global temperature decrease of about 0.8 of a degree Celsius for half a year. Research shows that aerosols such as sulfates can effectively reflect sunlight. They rise to heights of around 10 to 30 kilometers in the stratosphere, where they can remain for several years, providing a prolonged impact on the climate. Several technical solutions are being developed for delivering these aerosols to the upper layers of the atmosphere. One method involves using specialized aircraft, such as Boeing 747s or even drones, to spray particles with high precision in the desired area. Another approach includes launching balloons that rise to stratospheric heights and spray materials before returning to Earth. However, this technology has its own side effects. One of the main concerns is the impact on precipitation. Modeling shows that aerosol spraying can alter precipitation patterns, increasing rainfall in some regions and decreasing it in others. This can lead to droughts or floods, which in turn can affect agriculture and water resources. Another important aspect is the potential impact on the ozone layer. Studies conducted in 2015 show that sulfate aerosols can contribute to ozone destruction, increasing the level of ultraviolet radiation reaching the Earth's surface. Therefore, while stratospheric aerosol spraying can temporarily lower global temperature, this technology requires careful analysis and risk assessment before practical implementation. In 2017, a group of scientists from Columbia University proposed a protocol for conducting field tests, but many countries remain cautious about this technology. Technologies for capturing and storing carbon, known as carbon capture and storage, CCS, represent one of the most ambitious efforts to combat climate change. This process involves directly capturing carbon dioxide from the atmosphere, binding it, and storing it long-term, which requires the creation of infrastructure comparable in scale to the oil industry, but working in the opposite direction. For example, in 2015, scientists at the Massachusetts Institute of Technology developed a technology that uses special membranes to separate CO2 from other gases. This technology can reduce carbon emissions at the level of large industrial facilities. Specifically, in 2018, a carbon capture system was installed at a cement plant in Sweden, capable of capturing up to 30,000 tons of CO2 per year, equivalent to the emissions from 7,000 cars. The next step is binding the CO2. There are several methods, including mineralization, where CO2 is bound to minerals to form stable compounds. This process requires not only technology but also suitable geological formations for CO2 storage. For instance, in 2020, Norway successfully completed a program that injected over 2 million tons of CO2 into underground reservoirs at depths of over 1,000 meters. This storage is located in a geological formation formed over 100 million years ago, making it safe for long-term storage. However, to make these technologies work on a scale necessary to have a real impact on the climate, a wide network of infrastructure must be created, including pipelines for transporting CO2 from capture points to storage sites, as well as monitoring systems to ensure the safety of storage. In the United States in 2020, an initiative was launched to create carbon corridors that connect various industrial facilities and CO2 storage sites, enabling effective management of emissions. This will require billions of dollars in investments and coordination between different industries and government agencies. Clearly, creating such infrastructure requires not only financial resources but also time, as numerous studies and tests must be conducted to ensure safety and effectiveness. Statistics show that to achieve the climate goals set by the Paris Agreement, it is necessary to capture and store around 1 billion tons of CO2 annually by 2030. In this context, carbon capture technologies can play a decisive role in transitioning to a carbon-neutral economy. Healthy ecosystems such as forests, wetlands, and marine environments are powerful natural carbon sinks capable of significantly reducing the level of carbon dioxide in the atmosphere. For example, forests absorb around 30% of annual carbon emissions, making forest restoration a key step in combating climate change. Research shows that each hectare of restored forest can absorb up to 30 tons of carbon dioxide per year. Forest restoration in countries like Brazil, where tropical forest restoration programs are actively developing, helps not only in carbon sequestration but also in preserving unique biodiversity, including rare animal and plant species. Wetlands, in turn, serve as another powerful natural solution. These ecosystems can store carbon in the form of organic matter accumulated in water layers. For instance, a study conducted in Sweden in 2000 showed that restored wetlands can absorb up to 15 tons of carbon per hectare per year, making them important players in the fight against global warming. Additionally, wetlands help regulate water regimes, preventing floods and providing clean drinking water. Marine ecosystems, such as mangrove forests and seagrasses, are also crucial for carbon binding. Mangrove forests, for example, can absorb carbon 2 to 3 times faster than tropical forests, while seagrasses act as natural filters, cleaning water from pollutants. According to the World Bank, restoring mangrove forests can reduce carbon emissions by more than 3 billion tons per year. These ecosystems not only absorb carbon but also provide numerous other ecological services, such as preserving biodiversity, preventing soil erosion, and maintaining the stability of coastal ecosystems. For example, research shows that ecosystems with high biodiversity are more resilient to climate change and diseases, underscoring the importance of their protection and restoration. Therefore, natural carbon sequestration solutions not only contribute to combating climate change, but also support the health of the planet, maintaining balance in ecosystems. Restoring these natural systems is not just an ecological necessity, but also an economically viable step that can bring numerous benefits to humanity. It was calculated in 2000 that every dollar invested in ecosystem restoration brings back $2 to $32 in the form of ecological services. In the near-Earth space, there are constantly objects of various sizes, and this asteroid threat demands serious attention. Every year, Earth encounters numerous small meteoroids that usually burn up in the atmosphere, but this does not exclude the possibility of larger objects capable of causing catastrophic consequences. For example, in the 20th century, there were many events related to meteorite falls. In 1908, in Siberia, the Tunguska explosion occurred, when a presumed meteorite destroyed around 2,000 square kilometers of forest, leaving behind a strange and desolate landscape. Scientific research shows that there may be from several 100,000 to millions of objects in near-Earth space, including asteroids and comets, which periodically cross the orbit of our planet. Objects of size from 100 meters can cause global disasters if they collide with Earth. For instance, astronomers assert that an asteroid with a diameter of about 10 kilometers was the cause of the mass extinction of dinosaurs around 65 million years ago, which indicates the potential destructive power of such objects. Every week, scientists detect several dozen small asteroids approaching Earth at a distance of several 100,000 kilometers. For example, in 2020, more than 300 objects were registered crossing Earth's orbit. These data underscore the need for constant monitoring and study of the cosmic space to pre-evaluate the threat these objects may pose. A global network of telescopes and radars, such as the NEOWISE program, is engaged in searching and tracking these objects, which plays a key role in protecting Earth. There are also international initiatives aimed at data exchange and joint research, which is important in the face of a global threat. Asteroid danger is not just a scientific abstraction. It is a reality with which we live as our planet moves through space filled with potential threats. Astronomers assert that every day Earth is subjected to the impact of more than 100 tons of cosmic material, and only a small part of this meteorite shower reaches the surface. Meanwhile, the planet moves along its orbit around the Sun at a speed of about 100 kilometers per second, and this movement occurs in the presence of many objects that can at any moment change their orbits under the influence of gravity. Scientific research continues, and in the future, new technologies for protection against asteroids may appear. But for now, we live in conditions of constant danger. Scientists emphasize that understanding asteroid danger and active study of the cosmos are important steps in ensuring the safety of future generations. Each discovered object provides scientists with unique information about the formation and evolution of the solar system, revealing secrets that have been hidden for billions of years. It is important to remember that although we may feel protected on the surface of the planet, in space, numerous events are occurring that can pose a threat to us. Modern programs for detecting and cataloging near-Earth objects rely on powerful telescopes and complex algorithms that enable astronomers to systematically scan the sky for potential threats. Notably, the Pan-STARRS Observatory on Hawaii, which began operations in 2010, deserves mention. This telescope, equipped with high-sensitivity sensors, can detect even small asteroids approaching Earth. In addition to Pan-STARRS, telescopes like Catalina Sky Survey and Linear are also actively involved in the search for near-Earth objects. Each of these projects uses automated systems that process images, focusing on moving objects. Data processing algorithms such as moving object detection and asteroid detection pipeline allow for quick identification of changes in images at intervals of several minutes, which is crucial for early detection of potentially hazardous objects. When astronomers discover a new object, they calculate its orbit based on data about its position and velocity. This is done using a method known as astrodynamics, which allows for predicting the object's future location. The NEOWISE program, launched in 2009, also plays a key role in this process, using an infrared telescope to detect objects that may be too faint for visual observation. Each discovered asteroid or comet is evaluated on the Torino scale, which is based on the calculation of the probability of a collision with Earth. This scale takes into account not only the current orbit, but also possible changes due to gravitational interactions with other planets. For example, in 2020, astronomers assessed asteroid number 1281, which had a 1 in 800,000 chance of colliding with Earth. International cooperation is an integral part of these programs. Organizations such as NASA and ESA collaborate within the framework of the SpaceGuard initiative, which is focused on monitoring near-Earth objects. Annual conferences are held where specialists exchange data and methods, thereby improving the accuracy of predictions. It is important to note that thanks to modern technologies, astronomers have already catalogued more than 30,000 near-Earth objects, significantly reducing the risk of catastrophe. Currently, it is known that out of this number, more than 200 asteroids and comets have orbits that intersect with Earth's trajectory, and work continues on their study and monitoring. Defending Earth from asteroid threats has become one of the key challenges for scientists and engineers. Over the past decades, various concepts have been developed that promise to transform humanity's role from passive victim to active defender of the planet. One of the most discussed methods is the use of kinetic impactors. This technology involves sending a spacecraft at high speed to collide with an asteroid. For example, in 2021, a team from NASA and ESA successfully tested this method with the DART mission, where the spacecraft collided with the asteroid Dimorphos, altering its orbit. This was the first attempt to change the trajectory of a celestial body and demonstrated that such an approach could be effective. Gravitational tractors are another concept that relies on using gravity to change the trajectory of an asteroid. This idea was proposed in the mid-2000s and involves a small spacecraft remaining near an asteroid for an extended period, creating a small gravitational force that gradually changes its course. Scientists working in this area claim that achieving the necessary effect may take several years, but this is the least destructive method. For example, the Gravity Tractor project proposed in 2012 involves creating a spacecraft that would maintain an orbit around an asteroid using reactive engines to counteract the force of gravity. Nuclear explosions are also being considered as a potential solution. This method involves detonating a nuclear device near an asteroid to create a powerful shockwave that could deflect it from a dangerous trajectory. Such experiments require careful planning and assessment of consequences, and therefore they are a subject of much debate among scientists and ecologists. For instance, theoretical research conducted in the 1970s showed that an explosion at a distance from an asteroid could be effective without destroying it. However, such methods raise concerns about potential contamination and impact on the Earth's environment. All these methods are at different stages of development and require significant scientific and financial resources. In 2023, the European Space Agency announced the creation of a special program to study the possibilities of defending against asteroid threats, which includes both kinetic impactors and nuclear technologies. Furthermore, international cooperation is actively researching this area, highlighting the global approach to solving the problem. Scientific communities worldwide are beginning to realize that it is not enough to understand the threat. It is also necessary to actively work on its elimination. This creates an atmosphere of technological optimism, where humanity has the opportunity to become not just a victim of cosmic catastrophes, but an active participant in shaping a safe Earth environment. Success in this area could lead to significant changes in our perception of space and the safety of our planet. In the 21st century, space agencies such as NASA and ESA have been actively addressing this issue, allocating millions of dollars for research and development. For example, the NASA Planetary Defense Coordination Office was established in 2016 to coordinate efforts to study and protect against potentially hazardous objects. Scientists and engineers are working on new methods that could form the basis for a unified system to protect Earth from asteroids. Ideas are even being discussed about creating space stations that could monitor the Earth's vicinity and perform tasks to deflect dangerous objects. Currently, the discussion is not only about protection but also about the possibility of using asteroids as a resource. In the future, there may be a need not only to prevent collisions but also to use them for mining valuable resources. A strategy that includes protection and utilization of space resources could become the key to sustainable human development in the coming decades. In 2013, a group of scientists from MIT published a study that considered the possibility of mining water from comets and asteroids to provide resources for lunar and Martian colonists. Gradually, the concept of protecting Earth from asteroids is becoming part of a broader strategy for space exploration. The development of technologies that can protect our planet opens new horizons for humanity and underscores the importance of space research. Scientific achievements in the field of astrophysics and space technologies continue to open new possibilities for solving this important problem. Space threats from asteroids and comets have become a significant factor, uniting countries worldwide in the field of planetary defense. In 2012, more than 100 countries signed an agreement at the Tokyo International Conference on Planetary Defense to jointly monitor celestial bodies that pose a potential danger to Earth. This document laid the foundation for the creation of a global observation system, which includes major astronomical observatories such as Mount Lemmon Observatory in Arizona and Subaru Observatory in Hawaii. As part of this initiative, data exchange on discovered objects was established, enabling countries to respond promptly to new threats. For example, in 2015, over 300 new asteroids were registered through the data exchange system, which were previously unknown to scientists. A significant step towards international cooperation was the creation of NASA's Planetary Defense Coordination Office in 2020, which coordinates efforts of various countries in protecting against cosmic threats. Within this program, joint missions are conducted, such as the Double Asteroid Redirection Test (DART) project, launched in 2020 to test asteroid deflection technology. Joint research efforts, such as the Hayabusa 2 mission by the Japanese Aerospace Exploration Agency, aimed at studying asteroid Ryugu, demonstrated how international cooperation can lead to significant scientific discoveries and help in combating potential threats. The exchange of data between NASA and the European Space Agency resulted in over 100,000 images of asteroid Bennu, allowing scientists to better understand its structure and composition. Such efforts underscore the importance of overcoming political differences for the common security of all Earth's inhabitants. In the 2020s, the concept of planetary defense is gaining increasing attention in international politics, as the cosmic threat becomes a factor that can unite humanity. Scientific summits, such as conferences in Astana and Paris, gather scientists and politicians to discuss strategies for protecting the planet from potential cosmic impacts. In 2020, during the G20 summit in Rome, an initiative was officially proposed to create a global fund for financing planetary defense programs. This fund should support the development of technologies and scientific research aimed at detecting and tracking celestial objects. As a result of such initiatives, an international observation network was created involving more than 100 observatories and research institutions worldwide. This network not only monitors the movement of asteroids but also predicts their trajectories, significantly increasing the chances of preventing catastrophes. In 2022, the first international mission to prevent a collision with an asteroid was successfully conducted, uniting researchers from the United States, Europe, and Japan. The Planetary Defense Program requires countries to work together, as only through combined efforts can threats from space be effectively addressed. In this context, the creation of a global program for training and preparing specialists in planetary defense becomes an important step in increasing readiness for possible catastrophes. Scientific research shows that the threat from asteroids will not disappear, and humanity must be prepared for it. In 2023, a new research mission is expected to be launched, aimed at studying Comet Churyumov-Gerasimenko. This comet, known for its unusual characteristics, may provide insights into the formation of the solar system and the potential dangers it poses. Plate tectonics is a continuous process that has been ongoing for billions of years and will continue long after the disappearance of humanity. Currently, we know that Earth consists of 7 main continents, but according to the theory of plate tectonics, these continents are not permanent structures. For example, over the past 100 million years, continents have moved distances of up to several thousand kilometers. This movement is driven by convective flows in Earth's mantle. These flows generate a force that pushes the plate, causing continents to gradually approach or move away from each other. In the future, over tens of millions of years, tectonic processes could lead to the formation of a new supercontinent. Scientific models indicate that continents could begin to merge into a single large landmass, resulting in a significant change in climate, ecosystems, and Earth's geography. For instance, when continents merge, they form massive mountain ranges like the Alps or Himalayas, which arise from the collision of 2 plates. It is expected that this union will create new oceans and alter existing marine routes, which in turn will impact the lives of all organisms on the planet. Additionally, tectonic processes cause earthquakes and volcanic activity, which can catastrophically alter the landscape, as has happened in the past, such as the eruption of Krakatoa in 1883, which destroyed many islands in Indonesia and led to significant changes in global climate. In conclusion, over the next 100 million years, we can expect existing continents like Africa and South America to begin to approach each other, forming new geographical formations, including possible new oceans that will separate newly formed lands. This process is not controllable and will occur independently of human activity as tectonic plates move at speeds ranging from several millimeters to several centimeters per year. Ultimately, in 100 million years, continents may end up in a completely different position, and a new supercontinent could become home to entirely new forms of life, as was the case with the supercontinent Pangaea, which existed around 200 million years ago. Geologists and paleogeographers have proposed a hypothesis about the possible formation of a supercontinent called Pangaea Ultima in 250 million years. This model suggests that the current continents will once again unite into a single mass of land that could occupy a central position on the planet. According to forecasts, Pangaea Ultima will be located close to the equator, significantly affecting climate conditions. The average temperature in the center of the supercontinent is likely to be much higher than on the periphery, creating an extremely continental climate. Inside this landmass, there may be arid regions with minimal rainfall and temperatures reaching critical values. In contrast, the climate on its perimeter will be more mild and diverse, with abundant rainfall and vegetation. Scientific research shows that such geographical changes can lead to the emergence of new ecosystems adapted to changing conditions. Studies of plate tectonic models conducted in the early 21st century confirm that continents such as Africa and South America are moving towards each other at a speed of about 2 centimeters per year, strengthening the hypothesis of future unification. The supercontinent will have a characteristic shape resembling a giant shield with large mountain ranges formed as a result of plate collisions, which may rise several kilometers above sea level. These mountains will influence wind and rainfall directions, dividing climatic zones. Internal regions of the supercontinent may become deserts, while significant changes in ecosystems will occur along the coasts, where tropical forests and wet plains will form. One of the most prominent geographical features may be a massive mountain range formed at the junction of several tectonic plates. It is likely that this supercontinent will be surrounded by an ocean, which may take the form of a new, greatly enlarged Pacific Ocean compared to what we observe today. As the ocean expands, it may lead to the formation of new seas and bays, creating conditions for diverse marine life. It is important to note that such changes in the geography of Earth do not occur instantaneously, but require millions of years, meaning that if humanity exists during this time, it will encounter a completely different world. Considering current scientific research, it can be expected that Pangaea Ultima will have sizes comparable to the current African continent, which occupies about 30 million square kilometers. The formation process of the supercontinent will be accompanied by numerous geological phenomena, including volcanic activity, earthquakes, and tectonic movements, which will create new natural resources and alter existing ecosystems. The climate on the hypothetical supercontinent, formed as a result of the fusion of continents, will be radically different from the present one. It is likely to be characterized by extreme seasonal temperature fluctuations, which are due to the vast area of land and its distance from the oceans. For example, in the center of Ultima Pangaea, temperatures can reach 50 degrees Celsius in the summer, while in winter they can drop to -30 degrees. These temperature fluctuations can create conditions in which internal regions become almost barren. Moist monsoon winds blowing from the ocean coasts will provide life only in a narrow strip of coastal ecosystems where rainfall can reach 2,000 millimeters per year. In contrast, internal regions will suffer from drought, with rainfall not exceeding 200 millimeters, making them unsuitable for complex forms of life. Studies by climatologists show that such a climate situation can lead to the formation of deserts similar to the modern Sahara or Gobi. Meanwhile, biodiversity will be concentrated mainly in coastal zones, where ecosystems will adapt to wet and warm conditions. In these zones, unique plant and animal species may appear that can survive in conditions of increased humidity and temperature. For instance, in tropical forests that will form along the coast, one can expect the emergence of vegetation similar to modern mangroves, capable of surviving periods of flooding. At the same time, in arid regions, unique forms of life adapted to extreme conditions may arise. Some species may have the ability to accumulate water in their tissues, as aloe vera does. These changes in climate will also pose new challenges for ecosystems, as they will have to adapt to sharp temperature fluctuations and water scarcity. Research shows that changes in climate on the planet over millions of years have led to mass extinctions, and in the conditions of Ultima Pangaea, this may happen again. Scientific forecasts indicate that the number of species may decrease to a level where only about 10% of existing species will be able to adapt to the new conditions. Such changes in climate and biodiversity will have long-term consequences not only for ecosystems, but also for human civilization, which may be forced to find new ways to survive in this changing world. Considering all these factors, the climate on the supercontinent will be a key element in understanding the future of life on Earth. In a world where humanity has vanished, life on Earth continues to evolve, filling the ecological niches once occupied by humans. Approximately 5 million years after the disappearance of humans, ecosystems adapt to new conditions, changing due to climate shifts and catastrophes such as global warming and sea level drops. At this time, the mammals that remain after humans begin to develop into new groups of organisms. For example, rats and mice, which survived in urban ruins, become the main predators on new territories, adapting to various living conditions and forming new species with increased sizes and improved hunting abilities. Studies show that this can occur as a result of mutations and natural selection, leading to small rodents growing to the size of small predators like jackals. Simultaneously, in water bodies where fish once lived, changes occur in the ecosystem and new amphibians appear that adapt to life both on land and in water. These creatures may have characteristics that allow them to breathe both air and through their skin, giving them an advantage in unstable environments. Meanwhile, in remote corners of the planet where conditions remain stable, unique ecosystems are created with new plant species that can survive in conditions of increased temperature and water scarcity. For example, plants that extract water from the atmosphere, like some cacti, may become dominant on arid territories, forming entire forests of thick-trunked trees to retain water. In such conditions, new insect species may evolve to pollinate these plants, developing unique methods of reproduction and survival. It is not excluded that in the future, animals similar to penguins may migrate to new territories where the temperature becomes more suitable for their existence, leading them to occupy niches that were previously inaccessible. In this new world, the appearance of large predators similar to ancient dinosaurs is also possible, which adapt to new conditions and can hunt smaller mammals and even new amphibians. The formation of new ecosystems will depend on many factors, including geographical changes, such as the movement of tectonic plates, which can create new mountain ranges and change the climate, as well as changes in sea level, which can open new territories for habitation. As life develops on Earth, it is possible that we will see the formation of entire new groups of organisms with unique adaptations that allow them to survive in conditions that we cannot even imagine now. Evolution will continue, and even the most incredible forms of life may become a reality if changes similar to those we observe today continue on the planet. Scientific research, such as the work done by biologists from the University of Cambridge, shows that evolutionary changes can occur over relatively short geological periods, while ecological niches left vacant will be occupied by organisms capable of adapting to new conditions, leading to numerous unexpected results. Such changes in the evolution of life on Earth may demonstrate that nature always finds a way to restore balance, even if it takes millions of years. Changes on Earth in the distant future will occur under the influence of both internal processes and external factors, creating a breathtaking yet alarming spectacle. Internal processes such as plate tectonics will continue to shape the planet's surface. It is known that tectonic plates move at a speed of several centimeters per year, leading to the formation of new mountain ranges and fault lines over millions and billions of years. For example, the formation of the Himalayas began around 50 million years ago when the Indian plate collided with the Eurasian plate, and this process continues to this day. Ultimately, when continents once again gather into a single supercontinent, this will lead to significant changes in climate and ecosystems, creating new conditions for life. External factors, such as solar activity and changes in Earth's orbit, will also play a role. Solar flares can affect Earth's magnetic field, and changes in solar activity can influence climate, potentially leading to global cooling or warming. For instance, the Little Ice Age in Europe, which lasted from the 13th to the 19th century, was caused by significantly reduced solar activity, known as the Maunder and Dalton minima. Over billions of years, changes in the positions of continents will affect ocean currents, which in turn will influence the distribution of heat across the planet. This will lead to changes in ecosystems, the extinction of some species, and the emergence of new biomes. Oceans, which currently cover approximately 71% of Earth's surface, may change in depth and composition as volcanic activity and erosion continue. The increase in temperature and acidity of oceans caused by global warming is already being observed today, and in the future this could lead to mass extinctions of marine species, similar to what happened at the end of the Cretaceous period when dinosaurs went extinct. Over billions of years, as Earth travels through its cosmic journey, it will encounter asteroids and comets, as happened with Jupiter in 1999, when comet Shoemaker-Levy 9 collided with its atmosphere, leaving noticeable traces. These collisions can have catastrophic consequences, and history shows that they have already led to extinctions, similar to the hypothesis that an asteroid impact in the Mexican Gulf contributed to the extinction of dinosaurs. Ultimately, when the Sun's lifespan comes to an end, it will become a red giant, engulfing nearby planets, including Earth. The energy balance of the planet will be disrupted, and life as we know it will be impossible. Throughout its evolution, Earth will undergo numerous changes that will ultimately create a completely new appearance of the planet, and humanity, with its short history, will be just a small part of this cosmic spectacle. The entire history of humanity, which spans only a few tens of thousands of years, is but a fleeting moment in the context of Earth's billions of years of existence. The Sun, our star, is gradually becoming brighter, and this process has far-reaching consequences for Earth. Every 100 million years, the Sun's brightness increases by about 1%. This may seem insignificant, but over several 100 million years, such a small difference can lead to catastrophic changes in the planet's climate. According to astronomers' predictions, in 400 million years, the surface temperature on Earth could rise to over 100 degrees Celsius. As a result of this increase in solar radiation, the oceans will begin to evaporate, leading to a significant decrease in the level of life on the planet. Research shows that with the disappearance of oceans, which are the primary sources of moisture and oxygen, the biosphere will gradually shrink, retreating to the poles, where the temperature remains more tolerable. On the equator, where tropical forests and rich ecosystems currently thrive, conditions will become unbearable. As the temperature continues to rise, ecosystems that currently flourish will begin to collapse, and life will be reduced to the simplest forms, such as bacteria and archaea, which can survive in extreme conditions. According to climate change models, in 800 million years, the biosphere may not be able to support complex forms of life. Scientific research indicates that as the atmospheric temperature reaches 100 degrees Celsius, the level of carbon dioxide in the air could reach a critical point, making the existence of most living organisms impossible. At this time, Earth will resemble modern Mars, with its desert landscapes and cold poles, but with remnants of oceans that are gradually evaporating. By this time, the planet will have only rare oases of life in the most remote corners, where conditions will still be tolerable. Ultimately, as this process continues, with the Sun becoming brighter and hotter, the planet will lose its biosphere, leaving behind only desert landscapes and dead oceans. As the sun's brightness increases and the atmosphere is lost, the planet will witness its own death, as has already happened with other planets in our solar system. An example is Venus, where the greenhouse effect led to temperatures of over 200 degrees Celsius and an atmosphere consisting of 96% carbon dioxide. Due to global warming caused by increased solar radiation, Earth may be the next planet to face a similar fate. Changes in the activity of tectonic plates have long-term consequences for the state of the Earth's planet. When the internal heat of the planet begins to gradually decrease, the convection currents in the mantle slow down. Around 100 million years later, when the temperature in the core drops to a level insufficient for maintaining active convection, the movement of continents will stop. At this stage, the tectonic plates that once shifted and collided will freeze in a static state. The planet's relief will begin to even out, as erosion caused by atmospheric phenomena will smooth out mountain ranges and other geographical features. Over the next several 100 million years, without the formation of new mountains and volcanoes, the landscape will become unrecognizable. High peaks will give way to plains and hills, gradually disappearing under layers of sedimentary rocks. Geological processes that once created new elements and minerals will practically cease. As a result of this transition, the cycle of elements necessary for maintaining complex life will be disrupted. Without volcanic activity, which contributes to the release of carbon dioxide and other gases into the atmosphere, the level of oxygen and carbon will begin to fall. Over the course of trillions of years, when the activity of tectonic plates finally ceases, Earth will become a geologically dead planet, where life, as we know it, will become impossible. Ultimately, the cooling planet will resemble a lifeless shell, covered only by a thin layer of dust and remnants of old oceans. Changes in climate and the loss of biomes will lead to the disappearance of most forms of life, and ecosystems that once flourished will be destroyed. In the end, after several billion years, Earth will become an icy desert, where the only evidence of ever-existing life will be fossils and traces on the surface, lost in the vast expanses of time. At this stage, the biosphere as we know it will no longer exist, leaving only traces in the layers of sediments that future scientists may one day discover. In 5 to 7 billion years, the Sun will enter the red giant phase, during which its core will begin to contract, while the outer layers expand. During this period, the temperature in the core will rise to over 15 million degrees Celsius, causing helium to fuse into carbon and oxygen. As a result, the Sun will increase in size, its radius becoming approximately 100 times larger than it is now, and it will start to engulf inner planets such as Mercury and possibly Venus. It is expected that Earth will be within the expanding atmosphere of the Sun, leading to the evaporation of oceans and the destruction of the atmosphere. The temperature on Earth's surface will rise to 1,000 degrees Celsius, making it unsuitable for life. The water that once covered a large part of the planet will escape into space, leaving behind a dry and scorched surface. At this point, the enormous red disk of the Sun will occupy a significant portion of the sky, creating a spectacle that is impossible to imagine. Research shows that in this state, the Sun will emit light 20 times brighter than it does today. A planet once teeming with life will become a dead desert, with its surface illuminated by raging streams of light. Eventually, after several 100 million years in the red giant state, the Sun will shed its outer layers and become a white dwarf, leaving behind a planetary nebula composed of gases and remnants that once belonged to the star. At this moment, Earth may no longer exist as a planet, and its remnants may be lost among the debris and gas formed as a result of this grand finale. The Sun, which for billions of years has provided life on Earth, will complete its life cycle, leaving behind only a cold, dead world. The geological heritage of Earth is a captivating chronicle inscribed in the rocks, where each layer preserves evidence of catastrophes and changes that have occurred on our planet. These traces of catastrophic history form a complex mosaic of layers that have been formed over millions and billions of years. For instance, layers of sedimentary rocks can contain fossils of ancient organisms such as trilobites, which lived more than 500 million years ago, and through these fossils we can reconstruct the picture of life in those distant times. Volcanic rocks formed as a result of eruptions can tell us about the power of the Earth's crust when catastrophic events occurred, capable of altering the climate and ecology of the planet. These events, such as mass extinctions, have left deep traces in the geological record, allowing scientists like paleontologist Jack Horner to study how life recovered after catastrophes and what adaptations became necessary for survival. Each layer on the surface of Earth is like a page in a book, recording data on climate, geographical changes, and biological evolution. For example, tracking changes in the chemical composition of glacial deposits allows scientists to understand how the climate has changed over the last 100,000 years. Scientific methods such as radiometric dating allow for more precise determination of the age of these layers, which in turn helps create a chronology of changes on the planet. Mountains formed as a result of collisions between tectonic plates can tell us about millions of years of geological activity, their height and shape being evidence of processes that occurred deep within the Earth. Crystals enclosed in igneous rocks can preserve information about the temperature and pressure at which they formed, allowing us to study the history of planet formation at the atomic level. For example, research conducted by scientists such as Dr. Linda Z. Goodwin shows that analysis of carbon isotopes can reveal changes in the atmosphere related to ancient climatic catastrophes, such as the extinction of dinosaurs. Thus, when we study the geological heritage, we are not just looking at rocks, we are reading a history that spans billions of years of evolution, climate change, and the development of life. This underscores the importance of preserving geological formations, which serve as archives storing information about the past of Earth, how it was formed, the catastrophes that changed it, and how life adapted to these changes. Each layer of rock is not just a stone, it is a record of events that have become the foundation for everything we see today. Scientific research shows that in some regions of Earth, geological layers can reach depths of several kilometers, and these layers can contain traces of ancient oceans, deserts, and glacial periods. Complex processes such as erosion and deposition lead to the fact that the same rock can represent different epochs in the history of Earth. In this context, the geological heritage becomes not just a collection of rocks, but a true book, whose pages are constantly rewritten by natural processes and changes occurring on the planet. This heritage not only helps us understand the past, but also allows us to predict how Earth will look in the future when new catastrophes and changes leave their marks in this endless book. The study of ancient catastrophes is a multifaceted task that requires the use of various methods to reconstruct events that occurred millions and billions of years ago. One of the primary tools for this is isotope analysis, which allows scientists to determine the chemical composition and age of geological formations. For example, carbon isotope analysis helps to establish past climate conditions, as the ratio of carbon-12 to carbon-14 changes depending on temperature and the level of carbon dioxide in the atmosphere. Research conducted in the 30s of the 20th century demonstrated that changes in isotopic composition can correlate with mass extinctions, such as the Permian-Triassic extinction event, when approximately 95% of all species on Earth disappeared. Paleontological data also play a significant role in understanding ancient catastrophes. Scientists analyze fossilized remains to understand how life on the planet responded to catastrophic events. For instance, fossilized dinosaur remains found in deposits dating back to the end of the Cretaceous period indicate abrupt changes in biodiversity, which suggests the influence of asteroid impacts or volcanic activity. A study conducted in 2012 established that volcanic eruptions in India, known as the Deccan Traps, led to significant changes in ecosystems, as evidenced by findings in sedimentary layers. Geophysical research also provides valuable information about ancient catastrophes. Using methods such as seismic tomography, scientists can visualize the internal structure of the Earth and detect signs of ancient tectonic events. For example, in 2015, an international team of geophysicists conducted a study that showed how tectonic plates move and collide, leading to the formation of mountain ranges and earthquakes. They used data collected from seismic stations worldwide to create three-dimensional models that demonstrate how ancient catastrophes shaped the current state of the Earth. These studies require not only traditional geological methods but also modern technologies such as computer modeling and satellite imagery, which significantly increase the accuracy and depth of analysis. The use of highly precise radiometric dating methods, such as the uranium-lead method, allows for the determination of the age of rock formations with an accuracy of several million years, which is critically important for understanding the temporal scale of geological processes. For example, uranium lead analysis of samples from the boundary between the Permian and Triassic periods showed that it was during this time that one of the most significant mass extinctions occurred, associated with volcanic activity and climate change, as evidenced by findings in the Ural and Altai mountains. Scientists also use methods of ice core analysis, which allow them to obtain information about the composition of the atmosphere in the past by collecting data on the concentration of gases such as carbon dioxide and methane over hundreds of thousands of years. These data provide insights into how global catastrophes, such as ice ages, influenced the climate of the Earth. In 2009, ice cores were extracted from Antarctica, dating back more than 800,000 years, which helped establish a link between temperature changes and the levels of greenhouse gases in the atmosphere. These methods help scientists collect information like puzzle pieces to reconstruct the picture of ancient catastrophes and understand how they shaped the planet. The study of geological catastrophes offers us immense opportunities to understand contemporary processes and predict future events. The Earth has experienced numerous catastrophes such as mass extinctions, volcanic eruptions, and earthquakes, each leaving its mark in the geological record. For example, at the end of the Cretaceous period, approximately 66 million years ago, a mass extinction occurred, resulting in the disappearance of around 70% of all species, including dinosaurs. This event was likely caused by the collision of Earth with an asteroid, leading to global climate changes. Understanding the mechanisms behind such catastrophes allows us to better assess the risks associated with contemporary natural phenomena. For instance, studying active volcanoes like Vesuvius in Italy helps predict potential eruptions that could threaten the lives of millions of people. In 2012, scientists from the National Institute of Geophysics and Volcanology in Italy presented new data on potential threats from this volcano, using modern monitoring methods such as GPS and seismometry. Comparative analysis of historical data helps identify patterns, which in turn improves our chances of adapting to future catastrophes. Research shows that the intensity of hurricanes and floods is increasing, and this is confirmed by historical data on climate changes, such as periodic warming that occurred between 800 and 900 AD. The 18th century was marked by significant climate changes, as evidenced by data on sea level rise and changes in precipitation patterns. Scientists like Dr. Tony Levin from Columbia University argue that studying past catastrophes helps us not only predict but also prepare for future challenges. For example, data on how regions reacted to past climate changes provides insights into how we can adapt to contemporary challenges. There are also geological records that show how certain ecosystems recovered after catastrophes, suggesting effective measures. For instance, after the last ice age, which ended around 10,000 years ago, ecosystems in North America began to recover, allowing for the emergence of diverse flora and fauna. Knowledge of how nature recovers can aid in contemporary efforts to restore ecosystems after ecological disasters, such as deforestation or pollution. Research shows that many species that went extinct due to catastrophes were unable to adapt to rapidly changing conditions, serving as a warning for us. It is important to note that humanity itself creates threats to ecosystems, and inappropriate interference with nature can lead to consequences similar to those observed in geological history. Comparing current ecological changes with historical data underscores the need for a responsible approach to planetary resources. Thus, in recent decades, climate changes have become increasingly evident, as evidenced by data on temperature rise and changes in weather patterns. For example, since 2010, the average temperature on Earth has increased by 1 degree compared to pre-industrial levels, resulting in severe consequences such as extreme weather events and glacier melting. Each new catastrophe offers us a chance to learn and adapt, but only if we can fully understand the gravity of the situation and act on the basis of scientific data. In 2021, scientists recorded a record melt of ice in Greenland, serving as a wake-up call for the world. Such changes can affect sea levels, threatening coastal cities, and this in turn requires us to have a deeper understanding of the processes occurring in nature. Geological catastrophes such as volcanic eruptions, earthquakes, and asteroid impacts have profound philosophical significance, forcing us to re-evaluate our place in Earth's ecosystem and the universe. For instance, 85 million years ago, an asteroid with a diameter of 10 kilometers collided with Earth in the region of present-day Yucatan, leading to the mass extinction of species, including dinosaurs. This event, known as the Cretaceous-Paleogene boundary extinction, underscores how fragile life on the planet can be, dependent on random cosmic events. Understanding the constant presence of such catastrophic factors in our planet's history changes our perception of evolution. Evolution, previously seen as a linear process, now appears as a series of random changes where survival depends on the ability of species to adapt to new environments. The survival of mammals after the disappearance of dinosaurs when they were able to occupy the vacant niches in the ecosystem serves as an example. This shows that progress and the development of life are not always the result of directed effort, but can be the consequence of random catastrophes that open new possibilities. The influence of catastrophes on evolution can also be traced through volcanic eruptions, such as the eruption of the Toba volcano on Sumatra around 70,000 years ago, which caused global cooling and could have reduced the human population to a few thousand individuals. This event affected the genetic structure of modern humans and made us more vulnerable to future climate changes. Recognizing that life on Earth exists in conditions of constant danger makes us rethink not only our evolutionary history, but also our understanding of progress. We begin to see progress not as a guaranteed outcome, but as a fragile state that can be disrupted at any moment. In this context, the philosophy of necessity becomes particularly relevant. People increasingly ponder how they can prepare for future catastrophes and adapt to changing conditions. For example, in the year 2000, after the devastating earthquake in Haiti that claimed the lives of more than 200,000 people, the global community began actively discussing the need for the creation of resilient infrastructure and early warning systems. This led to new approaches in urban planning and disaster preparedness, highlighting the importance of human initiative in the face of natural threats. Ultimately, the recognition of the fragility of our lives in the face of powerful planetary forces underscores the need not only for scientific research into these catastrophes, but also for philosophical reflection on our place in the ecosystem. We must acknowledge that we are not the pinnacle of the evolutionary ladder, but rather a part of a complex network of life, where each event can lead to unexpected consequences. In fact, many scientists, such as Dr. Neil deGrasse Tyson, assert that the awareness of our vulnerability to natural forces should inspire us to adopt a more responsible attitude towards our environment. Catastrophes, however we may assess them, have always played a paradoxical role in the history of Earth. These destructive events, from global glaciations to massive volcanic eruptions, not only brought chaos to the planet's surface, but also opened new horizons for evolution. For instance, the mass extinction at the end of the Cretaceous period, when around 70% of all species on Earth disappeared, including dinosaurs, created unique conditions for the development of mammals. This process, known as ecological niche, allowed surviving species to occupy vacant ecological niches, forming the basis for the subsequent flourishing of mammals, including the ancestors of humans. An example of this is the evolution of primates, which in the changed ecosystem began to develop new adaptations such as bipedalism and an increase in brain size. These changes led to the emergence of new species, including Homo sapiens, who, as we know, became the dominant species on the planet. Volcanic eruptions like the Toba eruption in Indonesia, which occurred around 78,000 years ago, led to global cooling and a significant reduction in the human population to critical levels. Nevertheless, it was after this cataclysm that the rapid development of agriculture began, serving as a catalyst for the formation of the first civilizations. Around 10,000 years ago, during the Neolithic era, people began a settled life, leading to the emergence of the first cities and states. The destruction of old ecosystems and forms of life created space for new evolutionary experiments, as seen in island ecosystems like the Galapagos Islands, where unique animal and plant species evolved, found nowhere else on the planet. These chains of events underscore that every catastrophe, however destructive, becomes a catalyst for new forms of life. For Earth, continuity and cyclicity of transformation processes are characteristic. Each end becomes a beginning of something new, and historical catastrophes are merely temporary pauses in the endless cycle of life. All this confirms that the planet operates according to its own laws, where chaos and order intertwine, creating new opportunities for existence. Our Earth, with its billions of years of geological history, is an extraordinary example of how life continues to adapt and evolve. Lying under the starry sky at night, it is worth contemplating the magnificent history of our home in the universe, where the images of ancient catastrophes and rebirths can merge with our own dreams, creating new amazing worlds. In this context, it is worth remembering that Earth, having experienced countless catastrophes, continues to be a place where life finds ways to survive and thrive despite all the challenges.